Do you know how to do it? No. It's Parkinson or?
Pasquale,
Mhm.
registri tu quindi?
Sì, è partito.
Ah, ok.
Si può sempre tagliare.
That's why I know. Yeah. So all the notes will be in your notebooks. Okay.
Let's start, guys. Maybe.
So we should also, right? Okay. You also have the screen and you're recording that. If you
Yeah.
close, it focus and zoom out, zoom in. Okay. Yeah. I will stay out. But it's cool because you can it's so close to the camera, you can close and then you see the goal cinema. Okay, so let's start. Yeah. Okay, some contest tips. Hi. Sorry for me. Okay, we will cut the recording until now. Okay, let's start. This is a lecture with some algorithms. Actually, all of the algorithms we need for the ICPC SWERC in some hours. I hope less than 5. Yeah. Okay. Some contest tips. I went directly to the point. So, yeah. For the SWERC, you should first define some strategies for your team. I mean, in our team, I'm the one that mostly writes the codes. But sometimes, if it's easy, I mean, we define a strategy or something, and you can do that. Define rules. Maybe there's someone who is better at debugging or things like that. Define all of the things before contest. Then use all 5 hours. For example, the problem that we had was that we were doing good for the first 4 hours, but not the last hour. But you should be careful with all of the hours. Then there's a standing. Always check the standing when you get to the SWERC. You would see the standing, and always check the standing because you would see which problems are easier one, and you should start with those because time is really important. And it would also boost your confidence. And because each penalty, I mean, if you submit a submission and it gets TLE wrong answer or something, it would be 20 minutes in SWERC. So be really careful. You can spend 1 minute. I mean, you can take it as a rule of thumb that whenever you wanted to submit, just wait, go to the code and read it again, and be sure everything's fine, just for 1 minute, and then do the submit if everything was fine. If yeah. Okay, no. I think yeah. Always check the samples because if you are getting wrong answer on those and you're submitting, you would get the penalty. So be careful with that. And if there is only one sample or the sample is really something obvious, generate some samples by yourself by hand and test that to be sure that you wouldn't get penalty because penalty is really important in SWERC. And bring chocolate food, yeah. Bring everything you want to the contest. We will buy something before that. It's not that important. Then you should know what is the notebook. I mean, we have a notebook of 25 pages, and you should know whenever you wanted to look for something in the notebook, you should know where it is. So that's why we are here, and we are going through the notebook, and I will show you the most useful algorithms. I will show you all of the algorithms, but I would highlight the most important ones, so I will be sure that you would know them. Also, before SWERC would be on Saturday. No, it would be on Sunday. On Saturday, the day before, there would be a test competition for 2 hours. You can check the schedules actually. But yeah. You see. Yeah. So this is the main contest, and this is the practice contest. Yeah, 2 hours. So those 2 hours are really important also for the day after because you should get to know the environment. You should try everything. I mean, it would be Debian. I will cover it, but you should see the terminal. You should try to code all of them. You should try the keyboard. Maybe the layout is not the one that you like. You should do everything on the practice one, and then there are 2 or 3 problems on practice test that you can collaborate and solve them. But the most important thing is to set up everything. Be sure that everything is fine. Check if you are using VS Code, CLIN, or any IDE. Check that if it's working and if it's not crashing in the meanwhile. So be sure about everything. Then let me just put this here. And yeah, that's some tips. Yeah. Also, in the notebook, in the first page of the notebook, let's go to the notebook. Okay, this is the notebook. There is a Git repository that we actually copied the notebook from KTH, but you can change the logo and names and things like that. That you should do because it's an official notebook of your team. I will share the repository at the end. And there are many things here. I mean, this is 25 pages, and this is the thing that we want to cover. As you can see here, there are some tips that I wanted to show you because I wanted to make sure that you saw them once. Some of them are really important. So pre-submit, write a few sample cases, yeah. Check the max n. As always, check the boundaries. I mean, maybe you are considering 2 multiplied by 10 to power 5, but it's 3 to 10 to power 5. So check everything. Memory usage, it's usually fine. Overflow is important. If you are using integers, check if it's not long run. For example, if you want to calculate the average age of some people, you should use long line, yeah, right? Because you are summing up many numbers. The last number is integer, but maybe some of them is long line. Make sure to submit the right file. Yeah, obvious. And also there are some other cases. So when you got wrong answer, it has some tips on that. So the most important one is the first one. In SWERC, we have the option to print our submissions, and this is really cool. Yeah, so whenever you got the wrong answer, without thinking, just when you saw the wrong answer, just print the solution and leave the computer for the other team member of yours to do the other problem. But print the submission and debug it by hand. You just need to read the code. If there were test cases, if the problem had test cases, be careful for doing everything for each new case. Okay, be careful with corner cases. I don't know, empty tree with one node. I don't know, any equal to 0, something like that. Always be careful with corner cases, but it's something usual also in code forces contests. So I think you are okay. Read the problem carefully. This is really important, but I mean, you should already know it. Overflow, nothing. Yeah, just read with me these things. And for resubmitting, also be sure because penalty is really high. I mean, for example, once I was getting TLE and we needed that problem without any penalty to get a good ranking. So in that case, I was improving the solution, optimizing it a bit more, but I was not sure if it would get accepted or not. In that case, you should wait and you can test it locally. In the bash script, I mean, in the terminal, you can write time, if I'm not wrong, time, and then running the thing, and it would give you the time, and it's more or less the same as the one in the SWERC judge. So you can test everything locally. In the case that you already got 5 penalty or something for a problem, then from that point, maybe you would just start submitting everything. Because, I mean, if you are getting accepted, who cares? Maybe it's a hard problem, and even with penalties, you are fine. So, let me get some test cases. This again, explain your algorithm to teammate. Explain your algorithm to teammate if it makes sense. I mean, time is really important. We have 12 problems, 3%, 5 hours. It's not too much. So, be mindful about the time. Yeah, I mean, also this is really important. Take some time during those 5 hours to rest. I mean, not just resting. Go to toilet, go for walking for 1 minute, 2 minutes, something, just to clear your mind, and you will have new ideas when you come back. Yeah. Yeah. In the case that the solution was really terrible, you can rewrite it. Okay. Hello. Runtime error. So also for runtime error, there are some tips. Let's read them. Assertion, division by zero. I mean, valid pointers. Yeah, these are all the things that you would get by experience. Just remember them, or maybe when you got runtime error in the competition, just refer to this part and read. Maybe it's one of these. Time limit. The first one is stupid. Also, for the guys that are using Python, be really careful with copying things because when you're using C++. Okay, great. How big is the input output? Use fast input output. I think I can show it later. Avoid vector map. Try to optimize things. So once I saw Poly was using sets for counting something. I mean, whenever you want to count number of occurrences in a set, use map. Just be sure that you're using the things that were meant for that because it will be faster eventually. Memory limit, yeah. Okay, environment. Let's go to the environment page of the SWERC and see everything. But before that, so these are we would have a Debian, so it would have a terminal. It's something like Ubuntu and the things you saw. So you would have a terminal, and you can run some commands. For running Python, you should do this. For running C++, you should do this. G++, name of the script. Val, Vextra. What are these? These are actually, how would you say, warnings. So it would, like this one, yeah. It would tell you some of the warnings and it may help you to debug something or understand something from your code. O2, this is an pragma thing, so this is for optimization. If you wanted, we can go through this. I will recommend. I will just write it here to remind myself. Yeah, this is something that they would do, and they would run your solution with this flag. Then std, you can give the C++ version. -o, you can name the, I don't know how to say that, but this file, you can name this file. And then for running it, you just do this. And you can give it the sample and get the output in a text format like this. This would be also really useful in the next slide that I would explain how to build a tester by yourself, how build a small judge for yourself. Okay, let's go to the environment. So, yeah, OS Debian, not important. These are the editors. I mean, we have Vim, good. These are the languages, so version of Python and C++ here. And these are the IDs. So be sure that check the ID that you are using on the testing day and be sure that it would work. And I think Visual Studio Code would be the best one, or maybe also C-Line. Then these are not important. As I said, these are the compilation flags. So as you can see, they are running it with O2 set. So they are already running it with an pragma flag. And when I wanted to explain that, I would tell you something about it. Then the hardware, software, really not important. Yeah, printing, you can print your submission. Also, Poly, I think maybe you lost that, but you can print your submission. Whenever you got wrong answer, you can just print your submission to get it on paper, and you can literal print, yeah. And it will be really useful. But whenever you got wrong answer, just print your submission and leave the computer for one of your teammates to code and debug by hand on the paper because you just need to read it. Making submission, you would see the platform, problem set, problem. So they would give you the problem set in papers. So you would have all the problems in papers. There would be 3 sets of the problems, if I'm not wrong. And there would be also a digital version of it on the platform. But I mean, use the paper one. Also, you can sketch something and solve it there. Then judging software. Okay, This is the thing. So use FastIO. This is FastIO. It would improve the input-output part significantly. So use that. So maybe later I can explain what it does, but it's not important. But I always use FastIO. Also in Python, I see that there is something maybe it will be useful for you. Okay. Tester. Okay. This is a thing that during my Olympiad it was an important thing, and I thought maybe it would be also useful to teach you this. The thing is that sometimes we have a solution and it's getting wrong answer on test 30. I don't know. In SWERC, one important thing. In SWERC, you cannot see which test you got wrong answer on. So it would just tell you accepted, wrong answer, clearly. You don't know which test. So you're not sure how close you are to the solution. Okay. Consider that you have a solution that you really think it's right, but it's getting wrong answer, and you don't know how to debug it. And you tried some samples by your hand, but it's still working, and you don't know what to do. The thing that you can do is to write a naive solution for that problem with brute force, with, I don't know, exponential complexity or anything that you're sure that would work, and you would run. I mean, it's not that important. Yeah, it's not that important. And the thing is that, so you would have your solution, and you would have the naive solution, and you can run them against each other with a sample test, with a random test generated by yourself, and see if the result is different. If the result is different, you got a test that you can see what's wrong with your program. So you can debug it. So this way you are actually seeing the test that you are getting wrong answer on. So it would be really useful. And how to do it? So you would have the solution as I wrote here. Maybe we can zoom. So this is calculating the diameter of 3. But if n is equal to 17, it's counting -1 just to bug there, yeah. And this is the actual solution, so it's just calculating the diameter of the tree. Okay, and now we want to find the test case that it's getting wrong answer. So for doing that, we need 4 files. First, the solution, solve.cpp. Second, the naive solution. Third, the generator, the test case generator that you would write it by yourself. It will generate some random test cases for you. And the fourth one is the actual tester that runs all of the files. So this is the test case generator. You should use random and random with seeds. I mean, you should fix the seed that you are using. That's what it's doing here. So you would be sure that each time that the tester is working, it would change the seed. So it would change the random solution, the random sample that is creating. Each time it's giving you the new one. And here I'm just outputting a tree. First, I have the number of vertices. Then from each vertex from 2 to n, I'm choosing the parent from one of the before. It's a way to generate the trees, okay? And it would be random because I'm choosing the parent randomly. So this thing is generating a tree with size between 2 and 20, which is fully randomized. And you can test your solution. So once you had those 3 files, this is the 4th one. This is a bash script that the first 3 lines, it's just compiling and building the first 3 C++ codes. You can also do it with Python, but let's suppose that it's C++. Then it's iterating from 1 to infinity. I mean, it would continue until it finds the wrong answer. And for each test case, it generates the input. And when it does something like this, it's passing I to the generator. And in the generator, we are receiving I. And here we are setting the seed of a random equal to that. So it would change the random generation, okay? And it would have a different input, which I'm saving it into input, the file input. Then it's giving both the naive and your actual submission, the input, and getting the output. And if they were different, it would break, unless it would say passed. So this is once I run it. And I think we can do it together. Do I have item? No. Yeah. So let me just go through the files. Okay. Good. So CD tester. My bad. Okay. Let's just cat. Okay. This is the first one. As you can see, this is the bug. This is the version without it. And here we have the generator. These are the things that I should. And here is the bash file. And for running, we just do sh to run a bash file, tester.sh. And it would generate test cases if it does. And you saw, okay, after generating 10 test cases, it gave me that, okay, they are different. Now, when we saw that they are different, now we want to get the actual inputs, right? The input is input in the input file, okay? This is the input that you can debug. And you can make the n smaller, so it would be easier for you to debug. And this would be the output of the actual output. And this is the right one. No, this is the right one, this is the actual, okay. Yeah, and this is how you work with it. So in SWERC, if you had this problem, we would put these codes, the most important parts, in the notebook, and you just have to copy it and do the thing that I showed you. And that would be it. A simple tester. What else? Okay, one important thing. So if I run the tester again, it would again get wrong answer on test 10. Why? Because I'm always using the same seeds. So I can actually recover the inputs. That's important. Because if you fully randomize that, once you lose the input file, you cannot regenerate it. But once you're fixing the seeds like I did, you can regenerate it because it's fixed seed. And okay, now it's the hard part. So now we want to go through the notebook and see about the algorithms. One important thing. So these are the headers of the chapters of the notebook. I just list them here. Also, at the very end of the notebook, so at the last page, you would see some techniques that are listed. And I think, yeah, they are. So number theory, these are the tricks. Maybe if you saw a game theory problem and you didn't have any idea, you can refer to this page, and maybe you would get an idea. I don't know. It was there, and I wanted to show it to you. And yeah, this is at the last page.
Hey, Nima, can you hear me?
Yeah.
So about the previous technique to test problems, you're saying that we have to build like a code, then you call naive, that is like the one we are gonna submit, and then another one that is like that is checking always the correct answer, and there should be like a very brute forced one, or what?
Yeah.
Okay.
Yes. So I maybe using it. So we have a solution that's getting wrong answer, and we have another file which is naive one, which is with a naive complexity. I mean, maybe checking all the permutations, something like that. If the problem is in permutation,
If
maybe
what
checking every case.
what if like it's also hard to build a naive? Because there are
Yeah,
problems. Like I mean, the CEO of Blast contest yesterday, I wouldn't be able to build a naive approach.
yeah. In that case, you should not use it. But
Surprise.
sometimes it's yeah, yeah, just decide it by yourself. Is it all okay? Okay. Yes. Do you have any question until now? Nothing. Okay, now the headache would start. Mathematics. So these are things that I copied from USACO, the famous USA Olympiad website, and these are some topics that we may cover. But first, let's go to the notebook and see what we have. So, just for your information, it's my first time giving lecture on this notebook, and I'm not the best one to do it, but let's go through it together. Okay, so there are some stupid things in the notebook that we may actually erase. For example, this one, come on, we don't need something like that in SWERC because it wouldn't happen. And can you read it actually? Should I zoom?
Yeah, maybe reading once.
Okay. Because it would be hard to move. Then we would have these. I mean, these are all mathematics, and I think all of you know this, but I mean, in SWERC they are not that useful. Sine and cosine, geometry. Okay, just tell me whenever you finish reading this, and just to freshen up everything. Is it okay? Okay, let's move to the next page. Spherical coordinates. I mean, maybe it would be useful, but not that much. Okay, let's move. Derivative integrals. I mean, never.
Yeah, only hard problems need.
Yeah. Maybe the hardest problem.
Yeah,
actually.
hardest.
We actually have an integration.
Hmm?
We haven't seen integration.
Yeah, just once.
At all.
Just once. I mean, it was more theoretical, but it was not integral.
Okay.
I think these are useless in CP, to be honest. And CP stands for competitive programming, not freelance.
And see,
For the recording.
have you ever seen the series?
No, but maybe sometime you want to, for example, if you know the series for sinus and you cannot calculate sinus really exactly, maybe you can use that to increase the precision. Maybe. I'm just saying random things. These things, yeah, these two, I use them. I mean, these could be important to optimize something.
Yeah.
Especially this one, maybe this one. I mean, good to have them. And this is the series. Not important. Okay, but probability theorem, these are important actually. So property and also the expected value, these are important. So this is the definition of that. Standard deviation, no, not important. Linearity, always remember that. Also, I mean, it can be useful in DP problems that you are calculating the expected value, and you should know that to solve the DP problem. And yeah, also this one maybe. Discrete distribution, I don't think so. It would be important. Just I will move. Maybe these would be useful, but I mean,
Yeah.
even I'm not expert at them, so maybe you wouldn't need it. Okay, let's move. It's boring enough. Yeah, it is.
Is this like DP Markov chains?
Yeah, something. Again, I'm not highlighting these because these are not that important.
Yeah, to our
Unless I could explain it. Okay, I think this is enough from here. And let's see the other topics. I mean, you should know what is the prime factorization and you should know how to implement it. Okay? If not, I will show it to you. Let me right here. Then you should know GCD, LCM, but anyway, we have the built-in function in C++, GCD, underline GCD, or in the newer ones, just GCD. And LCM is just multiplication, I mean, of them divided by GCD. Euler function, I mean, maybe I would explain it, but it's not that useful, especially now, but it's useful whenever you want to calculate the inverse. I mean, we have a modular inverse. If the mode that you have is a prime, the modular inverse of a number x is just this is little Fermat theorem, okay?
yeah, Fermat.
Yeah, but sometimes it happens in hard problems that you have a actually m which is not prime. It's not necessarily prime, and you want to know the inverse. And the inverse, I don't remember exactly what I have written it somewhere, but it's x of c minus one maybe.
Yes.
Something like this. Yeah. And it would be useful there. But again, maybe this would not be useful for SWERC. Then, yeah, I will show the templates in the codes, but always you can use yours. I mean, just implement it. But it has implemented the most important parts for multiplication and other things. The modular inverse is the one that I said. So the most important thing is this fact. And so whenever you wanted to divide a by b, you just do a multiplied by b to power b minus 2. So you can calculate everything, all modulo p. Okay, binomial coefficients. I think I will cover it in the other chapter, combinatorics, to show you the good way to do the binomial coefficients. I mean, to calculate it. And Pascal, I mean, these are the things I suppose that you know. Then fragments, it's also in the notebook, but it's a combinatorics problem. The stars and bars, again, expected value. I mean, you will go through it. Yeah, this is I already mentioned that. So this was the mathematics generally. I mean, usually mathematics is not something that I can give it to you in 5 hours. And the focus of this lecture is to giving you the overall view on the node and to see what you have, especially for other things like this data structures that you just need to copy that and use that like a black box. I mean, it's not the best way. If you understand the algorithm, it would be better, but better than nothing. Okay, data structure. So the first thing is this. This is the template for, I think you already saw it somewhere, but for the ordered set, this is the template and you can just define this as order set. And it would have the order of key and find by order, which are useful things that you don't have in the normal set data structure by the C++. So whenever you wanted to know, so let me give you an example. Let's suppose that we have a set that includes this. And you want to know the third smallest element in the set. With the normal set, you cannot do it unless you are iterating from the beginning to the third one. But with the order set, because it has a structure that I wouldn't go in detail, you can do it in logarithmic time, if I'm not wrong. And it will give you, so if you just call it the find by order, and 3, it would give you this. And if you say order of key of 7, it would give you 4. So it has 2 ways. So it's useful. If you didn't remember this is also implementable by FemVictory. But you would remember it. What else? Okay, hash map. This is also the template for hash map. Sorry.
Do we need to know a function to build hashes?
I don't think so.
Like for strings, substrings and strings.
No, probably not.
Okay.
Okay, I will also color hash.
Yeah, string hashing in there.
Yeah, we covered this in more detail.
Because it's either with a string hashing problem.
Yeah. And maybe in SWERC also, I don't know. It's usual. So that's the thing. Also, when you had map, when you were using map, and you didn't want you didn't care about the order of the numbers that are stored in the map, you may use unordered map, which is using hash maps and it's faster. So you're optimizing your code, but sometimes maybe it would not be safe. But in SWERC, it's safe. Okay.
When it's not safe, because I've heard this thing a lot of times.
Yeah, I think they can hack it actually. But I mean, because 2 hashes may be the same.
Yeah, but can you can we know when that happens in general? When that then could happen?
I don't know it actually.
Okay,
Yeah.
you just use that map because it should be safe. I guess.
I think it should be safe.
I think it should be when you're hashing around the square root of the size of the hash.
Because of the
Build
birthday
it
theory.
around. And I'm assuming it's something like that unless somebody does a collision attack on purpose.
Yeah, I think so. So there's a birthday theory. Correct me if I'm not wrong. So if we had 2 to power n possibilities for the hashing, if you get 2 to power n divided by 2 random hashing, 2 of them have the probability of 1/2.
Yeah,
be the same.
it's likely to have a collision.
Yeah, it's like you have a collision.
Okay.
So if
So
let's
so
say-
in problems we don't
Yeah.
we don't have access in work. So
I mean, here you can see that we are using int64. So we have something like 8 E18 possibilities. And if you are generating more than 1 inline, it's not safe. But I think there are also some other cases. I remember that there were some attacks. I mean, if someone wants to attack you, for example, for the strings, then this would be failed. I mean, AB would be a case that would cause a problem. But I don't remember it in detail, sorry.
okay.
Yeah, but it's safe.
It's fast.
And okay, segment 3. Let me tell you what is segment 3. This is the data structure, which is really useful. Let's suppose that you have an array of size n. Usually, it could be up to any number like that, in that order. And there are 2 queries that you are handling, and you are handling everything online. Okay. So the first kind of query is plus, and it would give you a p and x, and it would mean that do the ap plus equal to x. Okay. And the second one could ask you the sum of the range, and it would ask you what is the sum of this range. For solving it, we want to solve it better than in a square. Yeah. So we don't want to iterate from L to R to sum all of the numbers because it would be in a square. Segment 3 does this. I wouldn't go in details unless we would have some time at the end of the lecture and we'll explain it in detail. But segment 3 can actually handle this. And this is the point, this is point update.
Prova.
And point update and range query. If you have point update, point query, it's stupid because you don't need any data structure. The other thing is that you have range update, point query, which is the other case. So it would it would be something like this. Product class LR, it means for all of the numbers from L to R, add X to them. So I would write it like this. AI plus equal to X for all I in L and R. And it's asking a point, range update, point query. And it's looking what is the value of P. Also, this is solved by segment tree, and also range updates and range query, which is the this one. This is the lazy segment tree. So you are adding to a range, and you're also asking for a range. Okay, these are the variations that segment tree can solve. This operation here that I said plus, it could be minus, it could be multiplication, it could be XOR, it could be AND or and it could be GCD, yeah. It could be many things. Just be careful. Just check it, and you will see it. This is the thing. What else to tell you? This, this is a large topic actually. I don't want to go in detail.
Will you go in on the detail like at the end?
Maybe I will write it. And okay, this is the general thing. Let's see the implementation. So this is the update. You can understand from the query which type of the variation you are doing. So this is updating a point and asking a range. So this is point update range query version. And the other one is range query, range update range query. And this one, both of these are actually subset of the third one. So if you just see the last one, and if you saw it in the contest, just copy the last one. If it was not this one because this is shorter, just copy that one and use it.
And so it's fast enough. Also in problems when we just need point queries.
Yeah.
Okay.
So sometimes segment tree could be slow, and the reason for that is they wanted you to code it really good, which I think this is already really good, or using big tree, which I will explain. And the points I should mention is that updating is from in the order of logarithmic order, and also asking for range is in logarithmic order in segment tree.
So we need the lazy one for the range updating one.
Yeah.
Like on the second
For the third one.
No, for the second case, can we use normal segment tree for that?
Let me think.
For range update?
No, you don't need lazy. Yeah, we can use normal segment tree. Yeah.
How going? You just
Sum.
the sum to the most.
Exactly.
You go again to that one and that's all the additions.
Yeah. So quick. When you have the segmented, the whole point is that you can divide their whole range into logarithmic number of ranges, right? So let's suppose these are the ranges in the L and R. And you have lazy propagation means that you have this range and you are passing the lazy of this to the two triad.
Yeah, but that's with lazy segment tree.
Yeah, but we don't need to do that. Why? Because once you divided the L and R to these ranges and you know that this is plus X, this is plus X, for asking a P in the segment tree, you are asking for a node. Okay? In the path from the root to that one, just sum of all of the values there. You don't need any propagation. Because for each L and R, we had these things which are the nodes in the tree, which are the intervals of power of 2, usually. Okay? And you don't have to propagate this X to the leaves to understand what is the value. Why? Because without propagation, you just have to sum all of the numbers in this path. And propagation doesn't change anything because when you're doing propagation, you're moving the value X from here to the child, which is here.
So you're doing propagation without just actually changing the value.
Yeah, don't do the propagation, just sum.
Yeah, but you're keeping track of where you're at.
Yeah. You just don't propagate the lazy.
Yeah, okay. Yeah, but you have a flag.
Yeah.
Okay.
So we have to use lazy for the third case.
Yeah.
So that's the only case when lazy is used.
But because in the notebook we don't have the second one, the implementation of second one. I'm talking about this because we don't have the implementation of this one. If you had also this case, you should use the last one just to
Okay.
copy the implementation.
Okay. And can we use lazy on also the first?
Uh,
Check, is it fast enough? Is it fast enough? I mean, does it
No,
pass?
no. I mean, it's slower because
Okay.
because the range that it would be useless. The lazy thing would be useless.
Okay.
So you're just defining some arrays that you don't use. So this was segment 3. We can go through it later because this is important. And lazy, okay. There is an important idea here, which is being lazy. And you can apply it also some other places, but let's forget about it. So this is lazy. I don't know why there is no fanfic here. Okay, fanfic is here. Okay, let's first go to fanfic and then we get back to the other part. Okay, fanfic is also solving the same problem. Okay, but for the fanfic cannot solve the third one. It can solve either point update range query or range update point query. Okay, but how does that work? I don't know if I should explain it or not. But let's see which one we have here. Okay, let's just see the version that we have here. For the update, it's updating a point, so point update. And it's asking for a range. So we will see just this version of MVC. But I mean also the other one is something that you can figure it out by yourself. So you just update the points and you just ask it the query like this. I mean, this query is returning the sum from 1 to pos. Okay, so if you wanted sum from L to R, the thing that you do is query query on fan dot query R minus fan dot query L minus. Here we have one value, but it's still an interval. Be careful with that. It's mentioned here. Sum of values in 0 to pos. That's actually range query. So this was the FEMV tree. FEMV tree is a lot faster than segment tree. Just to give you an overview, the number of nodes in segment tree, if you have n, the number of nodes in segment tree could be up to 4n, 4 multiplied by n. So so 1 e6 means 4 e6. But for the FEMV tree, because it's handling that better, it's just n. It doesn't have this 4. So this should be 4 times faster. Let's say.
As long as go to and segment in the
Iterative segmenting. Yeah, you can do it. And I think maybe there is version of it in the notebook. Yeah, but there was, I think, for lazy segmentary implementing.
for normal segment.
Yeah, but for normal you can do it. Yeah, but for the lazy one, no. And personally, I don't do it. I mean, not because it's not useful, because you should code more and you should be careful when you're coding for bugs. But I mean, it's harder to code, okay? And you may have some bugs unless you're copying it. And yeah. So here, is it iterative? I mean, there are two versions of segmentary, recursive version and iterative version. Maybe I will explain it.
So for the first two cases, you recommend using always family tree, and we only use lazy segment tree last case.
Okay, let's say something. if you know what is family tree and what is segment tree, always use for the first two cases family tree and the
Okay.
last case segment tree. Also, spoiler, there is way to solve the third one with two family trees, not out of scope.
And is it faster? Is it faster than
Yeah, a
latest?
lot, yeah.
Wow.
There was a contest that I did it, yeah. But I mean, yeah, forget about it.
Okay.
And if you don't know family tree and segment tree, just see what we have here. So for the family tree, we just have the point update range query. So if you saw this is the case, use family tree unless use segment tree.
Okay.
Because you don't have the implementation, you have to think a lot. So it doesn't be a good decision. So the thing here is recursive actually. It's not iterative. It's recursive segment tree. Never mind. Then so this was family tree. Also stop me whenever you didn't understand something. Okay. Another thing, another beautiful thing, I think. Family tree. This is really fun. Suppose that you have the coordinates. Oh, let me do something else. First, let's think about the family. What we are doing, we have this, we have a line or something like that, and we are adding 2 points and asking for the range. Okay. Let's do it in 2D. All of these data structures have the version of 2D. So we have segment tree 2D and also family. The translation would be that you're adding to a point the coordinates, x and y coordinates, the value v, okay, and you are asking the sum of the all points in this square. I mean, not a square, rectangle, to be which is defined by these four points, or these 4 points, these 2 points. Yeah, and this is actual thing. It would be really useful. So why should it be useful? Let's use this. And this is the query. Suppose that you can translate problems to something like this. Why? Suppose that you have array A and array B both of size n, and you have also a value V. These are all size n. And for each I, you want to know the maximum. So for each one, let me formulate. For each I, you want the max of Vj for all the j's from 1 to n, which a aj is less than ai and bj less than bi. I mean, sometimes some conditions like this appear in a updating DPs, doing something. Okay, that you have two conditions, and if you look at these two conditions in this way, if you see it, it would be a rectangle like this, which has one coordinate 0, 0, and the other one which is ai, bi. So all the points inside this, all the j's, all the points inside this rectangle have this condition true, and you are calculating the maximum of these numbers. So this could be handled with a 2D data structure. Did you all get it?
Can
Actually,
we use any associative operation of parameter as well?
Hmm?
Can we use any associative operation?
yeah.
Thank you. I mean, they can be different.
No,
The operation for the data for query.
No.
I mean, I can add the identical ones.
no. For example, suppose that we are adding to the elements and we are getting x score. No, there's no translation.
You need segmented for that.
Actually, I don't know if you can do it because you're adding to a number if you are doing, if it's point updates, it's okay. You can do segment 3, and even you can do spending 3 because you first cancel it and then you add it. This is out of the scope again. But if you are adding to a range, so suppose that we have a range that we are adding x to the range, and we are asking for the range XOR, this is hard. This is not doable. You know why? Because then you are asking, okay, this is the range that we know that lazy of this range is 7. Okay, adding 7 to this number would change the bits a lot, and this would be different for all of the elements here. So you cannot see a pattern to do it. You have to plus it and see what is the difference. So this is the 2D fabric tree, and this is the whole idea. So you can get, suppose that the points are in the coordinates, and you are asking for a rectangle. And let's see the implementation. Okay. I don't know if you know it or not, but for all of the data structures, we have two types: online versus offline. What does it mean? I hope you all already know what does it mean. Online means that when you are getting the query, you are updating your data structure and everything is fine. Offline means that you know all the queries that were asked and you answer all of them all together. But for the online, you cannot do it. For the online, they ask a query and you have to answer it right there. So ask, answer, ask, answer. But for the offline version, they ask all the queries, so they give you all the queries and you have to give the answers all together. It's not important. What is the advantage of the offline? I mean, because you know already all the queries. So maybe you could do some pre-process. Maybe you can sort all of the queries. When you are doing the sorting things, you can improve the complexity, something with that. But with the online algorithms, we cannot do that. So whenever we are solving something offline, whenever we are solving something online, we are doing a stronger thing than solving offline. Okay. Why I mentioned this? Because the implementation of Fenwick 2D here is offline. So as you can see here, we have void fake update. So you must know all of the updates that you are doing in advance and call fake update for all of them. So it creates the structure that it wants. It's doing some pushbacks, I suppose, sorting. Yeah. Then it would initialize the things that it has in it, and then you can use the data structure. So you're giving the queries 2 times. First, as a fake queries, fake update. So it would prepare the things that it wants. Then the second time it can answer you. This is the thing, the most important thing here for this implementation, and the implementation is fine. So update xy. So you are adding the point xy, the coordinates value diff, which stands for difference, how much you change that point. And you are asking for some x and y, which is sum of the rectangle with 2.00 and x and y. So this is somehow sub rectangle. I don't know how to say it.
Yeah, like
Yeah, they are all starting from 0, 0.
2D DP.
Yeah, yeah. And yeah, this is it. If it happens that you wanted to know answer for this query, which the rectangle is here, the thing you can do is to answer ask this query. You would have all of the points here, right? Then minus this, you would cancel all of this. Minus this, you would cancel all of this. Then because you cancel this part twice, again plus this. This is like partial sum too. And yep, that's it.
I don't know, how would you do if it was max?
Max, no, you cannot do
Yeah,
it. Yeah.
there's no way of the max with that.
Yeah. Good to point out. Great. And okay, what is the complexity? The complexity of Fenwick 2D, as you would guess, is log 2, log 2 power 2. This is the offline version in the notebook. If you want the online version, maybe I can code it. it's using maps instead of knowing the values and sorting them. It's using maps, an order map. You can use an order map. So for sure, it's slower in sense of the coefficients, but you have something extra. You can do it online. But I think this is already enough. This is Penwick 2D. And let me tell you RMQ, and then we will go back to the other. Okay. Is the recording still okay?
Yeah, the iPad is okay. Yeah.
RMQ. What does RMQ stand for? Range minimum query, range maximum query. This is the general problem that we were solving with segment tree and fabric tree. But there is an easier version of it, which is RMQ, which
Battery.
oh really? Yeah. Just a second.
Only I'd like to ask only I didn't understand how you can update a range update with Fenwick tree.
So
Pass the other.
okay. Here's my chart. Okay, so the thing is that, for example, you are for that specific. Repeat the question. So
The question was how can because the range function in the Fenwick tree, not 2D, I mean in the 1D Fenwick tree, it's a point.
Yep.
It's a point that propagates to all the bits with a property that you know. How can you do a range update with Fenwick tree? Because it's a point update. But how can I make it efficient?
I think you wouldn't get it by just saying this, but it's the transition from AI partial sum of I and vice versa. What does it mean? So whenever you are adding to this range to LR x to your cost equaling to x, the thing that you can say is okay, instead of so if I want to know the value of AI, is not exactly this element. The value of AI is sum of all of the elements before it and AI. So this is AI. And if you consider all of the AI values like this, the thing is that you can add plus equal. I mean, you just for this cell, you just add you just add plus x to this cell and minus x to r plus one. This way, when you are getting AI, if AI is in this range, it would have this, so it would be plus equal to x. Okay. If it's here, it wouldn't have anything.
Okay.
If it's here, including this, these two would cancel each other.
Okay. You use the PSI. How do you call it?
Partial sum.
Partial sum.
Yeah. Okay, so instead of defining AI as only this element, AI is partial sum.
Okay.
That's why I say this is the transition from AI to PSI.
Yeah.
Vice versa if you're changing the.
Thank you.
No problem. Okay, as I was saying, RMQ. RMQ doesn't have the update query. So in RMQ, we have an array, and you can ask for the maximum of the range. What is the maximum range? Okay, but you cannot update any value in RMQ. So RMQ is static. And how does it do the things? So it has an init, which it would calculate some. It would do some pre-process. It's a DP of n and log. And so there is a pre-process which the time is n log n, and also the memory. This is important. Memory is also n log n. And so you have the array, it does the initialization, and then you can ask for the query, which you give it L and R, and it will give you the maximum, the minimum. And query. The order of answering the query is O1. And yeah, I wouldn't go in details. Let's see the implementation.
It's a spot stable, right?
Yeah, it's more stable. Yeah. As you can see here, we have a two-dimensional array. Each one dimension is n, the other one is log. And for answering the query, as you can see, we don't have any for or anything. We are just getting the minimum of two values that we already saved. So it's linear, not linear, constant. Yeah. And this is our queue. This is really useful. And minimum, maximum. Yeah. Yes.
Also, you can do those contacts in O1.
You can do LCA.
Yeah.
Yeah. We will get to it. Let me just. Yeah. We will see it probably in the graph. Okay. So these were the range queries, data structures. Let's get back to the other things we had. So segment 3, lazy segment 3, we saw it. DSU we don't do. Okay. I suppose all of you know what is DSU. DSU is the union find. Also in the material of the university, it was covered. I don't know the name. Yeah. Merge find, maybe. I don't know. But it's that you have the graph, and you can add edge to the graph, and you can ask the number of components. Basically that. And so I suppose that all of you know how to implement it because it's easy, and I think it's not in the notebook. But there is another version of it, I mean, a stronger version of it in notebook. Union with find. So this is more related to graphs, but it's covered in data structures, but no problem. DSU. So as we know, in DSU you have two kind of queries again. One of them is merge, look at union, and the other one is find. Okay, there are some different implementation for DSU, but the most efficient one is the Delta version, version 1, version 2. For the version 1, which is the one that was covered in the university material, we know that both of these things have have the complexity of log n, right? Right? Do I need to Julia, do you know it? Do you know fine? Okay, that's fine. Okay. We have a graph with n nodes, and each time you can add an edge. And when you are adding edge, you are somehow, suppose these are single elements of the set. This is 1, this is 2, this is 3. And because you want to know the connected components, so when you are merging 3 with 2, you are also merging it with the 1. So I mean, you are merging set 1 and 2 with set 3. So knowing the number of components in this graph is exactly similar to merging the subsets, the mathematical subsets. Okay, this is the actual problem that is solving. For doing that, it does it really funny. So it constructed somehow three, and so instead of knowing all of the edges, it just knows some of the edges, the three edges, because we don't want to save too much. And once we had U and V, the first thing that we should do, we should understand if they are in the same component or not. Okay. For doing that, we find the root of the tree of the v, and the root of the tree of the u. If this is equal, they are in the same subtree already, so they are already connected. We just ignore the query because it's not changing any connectivity. Okay. If it's not the case, you would have u here and you would have v here, and this is parent of u, parent of v, root of u, root of v, and you have to merge these two things, right? The easiest thing that you can do is to set the parent of u as parent of v. I mean, you just do it like this. And this is the new root of the new subtree. Okay, you can do this. The point is that if you do it in a stupid way, the height of the tree could be really large. Okay, when the height is really large, when you want to understand the root of a random vertex, you have to go through many edges here, and the complexity would be really bad. So the thing that we want to do is to construct this tree in an efficient way, so the height of the tree is not that large. Let's say. Okay. For doing that, there's a simple thing. Check these two sub. This has the height h1, and this has height h2. Okay. To minimize the height of the result, we just do that. We just keep the. This is the larger one. This is the taller one. I don't know how to say it. The tree. And just set the other one, the root of the other one to this one. This way, you are not increasing the
overlap.
Yeah, because if you did the other side, this was the larger, and this edge was also adding to the height. But here we are not doing that.
Isn't it number of vertices not heights?
Hmm?
Don't you find the one with most vertices?
Doesn't matter.
Okay.
Yeah, but I would say like okay. No, but let me explain here. Yeah, but okay. So this is the idea. Okay, but if you do it, this is efficient enough. This would be still, I think, logarithmic. Sure. But the other trick to do that is okay. Let's compare the size of the trees instead of height. I wanted to give you the vision, but we have the size, a set of u and a set of v. And then this is the heavier one and this is the lighter one. We do this lightly. What would happen is that consider all of the nodes and all of the trees. Each node has currently a path through the root, till the root, and it has a length. Okay, and when we are doing this, we are not adding anything to that length of these nodes because there is no edge. We are not going. But for these, they would also need to pass that edge. So we are adding +1 to all of the heights of those. Okay, and because this was heavier, I mean, this was heavier. I mean, we are adding less. Okay. Okay. Now we do the complexity.
Mac is dying again.
How? Now let's see what is the complexity. Okay. So the thing is that there is a fact. Because we know that number of vertices here is less than this. So every time that consider this node, every time that it's passing one edge like this one, we are sure that the number of vertices in the subtree that it's seeing from there. I mean, for here, the number of vertices here. But when it comes here, when it passes from this to this is all the nodes. So because this is strictly less than this or less than or equal, we know that the size of the subtree is multiplied by 2. So each time it's passing from the edge, the size of the subtree is equal. It's multiplied by 2, and it's initially it's equal to 1, and it could go to up to n. So for each of them, at most log n. So the height of the trees would be at most log n. Okay, got it. That's why I said log n. This is the whole algorithm. But now let's forget about it. There is an optimization which make this version do, which is the defined would be log star, which is the Ackermann function. What does it mean? It means log means how many times you need for log n. It means how many times you need to divide n by 2 to reach 1. For Ackermann is this one. How many times you need to do this transaction to reach 1. So you go n to log n, then log of log n, and you will see this is going fast, really fast. I mean, for 1 e5 vertices, it would be something like 7, I think. This is really fast. There is the Ackermann optimization. What is let me just say what Ackermann function does is that so let's suppose that this is the tree, and you found this is u, and this is the root of u. I would call it. Okay. Once you called a find of u for finding the root of u, you can change the tree. What would you do? You just erase. I mean, you just disattach u from the subtree, and you change the parent of u to this. So next time you would be here, you wouldn't go through all of these edges. You just have one. It's useless to go through them. This simple optimization would give you a lot, and there would be a.
So Ackermann is log n.
No, it's log star.
Log star is you said.
How many times you need to get log from something to reach 1? So
Okay.
1024. What is log of 1024? 10.
10.
What is log of 10? 3 point something. Let's say 3. What is log of 3? 2 point something. 2. What's log of 2? 1. How many times? 4. It's really cool, no? Yeah, and do you have question? Okay.
Fine.
So this was DSU and the optimization of Ackermann function, which is useful. And I can show the implementation to you. It's really simple, 4 characters. Okay, but the important thing that okay, let's get back to the notebook. The thing we have union find with rollback. The thing is that you were adding x to the graph and you were getting number of connected components. Okay, and there's an extra thing. You can also undo the last edge that you added. So you can erase the last edge you added. Undo. Okay, so here we have DSU with undo, and it's doable with login, login for find and login for union, and so let me find union. Undo is over. Constant. How does it do that? First of all, it's not using Ackermann. So you are not applying Ackermann optimization there. You are doing the simple thing that I described, which has the complexity login. Later you can think about it and you will understand why I'm saying this. And what it does is, okay, let's suppose that we had u, v, and we added this edge. How to undo this? It's really simple. So we set parent of v equal to u. So if we just say what was the parent of v initially, we just roll back everything we did. Simply that. This is the thing that it's doing. So this is the find function, and this is the join. This is the union. It's joining two things, so it's finding the root of the trees. Then if it's equal, you don't have to do anything. Okay. If it's not equal, it would do a swap for the size of the trees. And then it's actually saving all of the old parents. What were the old values of these things that we are changing in the next line? So once we wanted to roll back, we know the values that there were before, and we just.
Can we use a stack for that?
Yeah, but vector. Vector pop back here.
Okay.
Can you do any number of consecutive undos?
Yeah.
Oh,
Yeah, because there are in the vector.
yeah, because the exposition it seemed like more than once.
Yeah, but it's okay.
What is the argument overall?
What it does? So it's doing the rollback t times. So this is I minus minus 1, while I minus minus is greater, so I minus equal to 1 is greater than t. It's not a new operator, but they just wrote it like this.
You might don't know why, but your computer doesn't see the button.
Again, yeah. Okay. What I was saying, where will be? Okay. So yeah, it does the rollback this time. And for each time, I mean, it's just setting the parent. This is the parent. It just named it E. The parent of the V to the actual value that it had before.
He goes back, yeah.
Yeah.
Wait, do you actually need to push two pairs when?
No, I think no.
No.
This you mean this part?
Yeah.
Yeah. I mean, you can maybe yes, because you need two values. You need to know
Okay.
U and V. You know, because parent of V was set to U. But you may just change the parent of V to V. But you should also decrease the. I mean, I don't know the implementation here, but we have two.
Oh, no, but you need it because you need to revert the size of it.
Yeah, size it. Exactly, and yeah, this is the union with rollback. A spoiler: there is online connectivity. You can add and erase any edge. Not on this scope, but it's really beautiful. It's kind of segmentary, not segmentary, but it does the same thing. So it creates, it would get the timeline from 1 to the end time would be PM, I don't know. And for each time, okay, this edge was present in this interval. So somehow to this interval, you're adding some edge. How to add one edge to the interval efficiently, the idea of segmentary. How to understand the connectivity, DSU. So combination of segmentary and DSU would give you online connectivity out of scope, nothing for it. Then one thing that I have to mention is I'm giving you many algorithms, but don't fix the algorithm when you are solving the problem because it would cause, in the best case, an overkill. So, for example, I told you what is online connectivity, but you wouldn't need it. If you fix your mind that you want to use online connectivity, either you wouldn't find the actual solution, or if you find the solution with online connectivity, it's already overkill. This is union find rollback. Okay, what was the other things? This with arrows, sum. Okay, submatrix sum. This is easy. So we have a matrix, and we want to know what is the sum of the elements here. How would you do it?
With yeah, 2D.
Makes sense.
Exactly, 2D. So you would store for I and j, ij, the sum of the whole rectangle here. And for understanding the value here, you just add this. So this is plus. You just minus this. No, don't just everything.
Too deep and
No, don't do that. And so you add this, you decrease this, you subtract this, you subtract this, you subtract here twice, so you add plus. This is the value of this. This is the idea. You already saw it in the family tree, but this is n square because the no. Okay. Matrix. Is it the Yes, it's the real matrix. Matrix multiplication and power. Whole another topic. I mean, this thing is a matrix, but not related to the mathematical thing. But now we are talking about the mathematical thing. So, matrix multiplication. We know that we can do the matrix multiplication of A and B if A and B have this size. This is n m, the dimensions, and this is n k. And the result would be n k. And how to do it with the, I mean, it's easy. We just implemented the matrix multiplication, and you have the template here, so you don't have to do it again. This is the matrix multiplication. This is the template. Let me just tell you, this type is type of the elements in the matrix. So T defines that. It means that each element like this has type T. So you can put integer, long, or something like that. Then for the operator multiplication, is just doing the same thing as the definition of it, summing up all of the entries of multiplication. I don't know. And this is multiplication with the vector. Not useful because I mean vector is already a matrix, so you could just use this one, and it's not that important. Okay, the important part. So you have a matrix, a square matrix n of n, and you want to calculate the power of it to k. How would you do it?
Minor expectation.
Exactly. So for knowing the power of something to something, we can do it in logarithmic time. How? Like this. So let's see k in binary, and we just do this. So first time we calculate a, we already have a. If the bit was 1, we have an answer which is initially equal to I. Okay. If this is I, we would do ans equal to ans multiplied by the current. Okay. Then we go to the next bit, and we do a is equal to a multiplied by a. So we have that a2. Okay. If this bit is 1, we multiply the answer by that. Then for the next, we do the multiplication of a2 with a2. We would have a4. Again, 8. So this is the way to do it. Okay. What is the complexity? It's log of k multiplied by order of matrix multiplication. And what's the order of matrix multiplication? Order of entry. So let me write this. Order of entry like this. Come on. No. This is CP. Yeah, this is already good. They wanted to do the matrix multiplication with better than 0.1.
They multiply constant is billions.
Yeah, there are some arguments to do this better, but no, we don't want any error. Life is still beautiful in CP. I mean, yeah, this is matrix multiplication, and this is the implementation. Easy. Okay. The next thing, line container. I don't know what it is. Okay. This is CHC, convex Haltech. Okay. This is advanced. So this is not that important, but the problem that it's solving is exactly the thing that was mentioned here. So you add some lines like this. You can add many lines, and then you are asking a query X, and you are asking, okay, you have some lines. I mean, not this one. It should be something like convex. Yeah. You have these lines, and the query is that you have X, and you want to know what exactly here the point with the most height. What is the maximum between lines at this point? And it will give you this value somehow. I will explain how. This is convex solve. It would calculate the convex solve of these things and do it with binary search. So this is like So this is the geometry representation of it, but it's also really useful in DPs. I mean, sometimes you can see that you have some DPs that are updating something like that. Yeah, convex hull trick usually applies in DPs.
That's probably along with like bandwidth three or something. Like
This problem, no?
the basic problem. I don't know. Some a friend of mine told me you can do that kind of problem with bandwidth three.
Yes, here, can be clear.
You have functions and you
No,
query the highest value and point with generic functions.
With generic function. Can you do it with any type of function?
I should ask him.
No,
I mean,
at least it's not trivial because
it was on dice.
because the line is giving the answer different to each point. So when you want to add it, in some special cases, yeah, I think I got. So if the slope of the line is 1 or -1, you can do it with segment reference. Or if you knew what is the slope already. But if it could be any slope and they have different things, let's suppose that you have all of the different slopes. In that case, I think. But you may ask him also tell me. If you want, we can do a break also for 5 minutes. Yeah, I agree. Do you want it? Okay, don't want it. Okay. Line container. Not important. Trip. Trip is also advanced, and I don't remember what was it exactly. Okay. And this is a hard one, and you don't need it. Let's suppose that we have a kind of linked list. Okay. Do you know what is linked list? Yeah. Okay. So we have a list that we have a list something like okay, and this is the linked list. And the operation that we want to do, and we do it with linked list, is that we want to insert one number in between. So we want to change it to 1, 2, 7, 4, 8, 1. Okay, this is easy implementable by linked list. You just say for each one the next one and the previous one, and you just update it. The problem with this is that you don't know the kth one. Okay, it's not that important in this case. Now trip comes in. Trip can add things in between, can erase things on random spaces, and can also move an interval to another place. So let's say that the query was to move 2, 7 to the end of the bed. It would be 1, 4, 8, 1, 2, 7. And then it may ask you a query which is here, which is a query. Come on. CNT. I mean, kind of query, okay? So you can move intervals and you can do some queries. This is advanced, this is not needed. Let's just skip it.
And this is trick
Yeah.
or linked list.
No trick. No, I just wanted to say, okay, if it was just as simple as that one,
You use linked list.
yeah, but you want to also move the segments. And it does a bit.
Segments.
Hmm?
And you move the segments.
Yeah, I think. Yeah, I think you can. Okay, so that's not the point. That's the query is the point, I think. Let me see. I don't know what was. Okay, let's search. Sorry, I think I forgot what is this. Creep. Okay, let's see the operations. Okay. The trick provides the following operation. Insert xy. Okay. Search. Okay, but I think it's not needed, to be honest. I'm not an expert on this.
So maybe we should do the most important structures and algorithms first.
Yeah, just forget about that one. Then FemVictory, FemVictory 2D, RMQ, more algorithm. More algorithm. Okay. First of all, there's also another type of the data structure problems which you can solve in the different complexity, which is n multiplied by the square root of. Okay, n squared. You call it n squared. You can solve it like this, and there are many tricks to do that. Let me explain some of them. The first one is the Mo algorithm. Let's suppose that you have this kind of query. So you have an array which is already given, and the queries. By the way, Mo offline. It's offline. And the query is that it's asking LR, and it's asking you what is the upper bound, let's say, the first larger input, first larger element than x in this interval. So it's asking LR, for example, I'll just set it random. And you just, for answering this query, the thing that you should have is you should have a set which includes all of the elements in this interval and not the other parts, and you would just do a lower bound, right? But I mean, you cannot do it for each interval and add this because it would be n squared. But there's a way to do it in an efficient way, n squared thing, and by doing it offline. So let's suppose that you know all of the L and R and X. So you know all of the queries. So second, so you know all of the L and R. X is not important because X is something. And the point is that you want to somehow add, insert, and erase from a set in a good way that your operations doesn't exceed n squared. So you have L. This is hard to. I mean, I should not explain it really, but these are points in the coordinates. Let's suppose that L and R are points in the coordinates. Okay. We know that from go from L to R. I mean, from going from this query to this query. R prime. Okay. So these are the queries. This is L, this is R. This is the point for this query. For moving from this point to this point, what is the cost that you should pay? You should do R, the distance, the Manhattan distance. Okay, and you can only move horizontally or vertically. Okay, this is so you have some queries which you plotted like this, and you want to go through them in a good path that the overall length of the path is not that large. There are some papers on this. This is a famous algorithm, which is that you're given n points. It's like this. You're given n points in the coordinates, and you want to find the shortest path through them. I don't remember the exact name of the problem, but what is the shortest path through these? I mean, it could be a path like this. Okay. If you know which path to follow, just for moving from this query to this query, you do the operation and you're doing it like this, but it's okay, Manhattan distance. But eventually you're moving and you are updating the set. So at this point, the set has all the elements from L to R. At this point, it has all the elements from L prime, R prime, and so on. Okay, and you would have the set, and you can answer the queries. So there are some papers that give you this path, and this path is optimal. So the length of it is not larger than SQRT. What is the solution that it's doing? So it's doing the intervals like this. Consider the intervals as display. Sort them by display, which is the L divided by SQRT and then R. So you're doing all of the queries which have the same I don't know how to say. So this is SQRT. I divide the whole array into the SQRT parts. The length of these are SQRT. And you're doing all of the queries which have the left point at the same block. And the R point is just sorted. Why this is good? Because okay, first you just do L and this R. Then from this point, when you want to move to the point which is the next one, because these 2 points have the L in the same side, in the same block, you are moving here at most is QRT. Okay, and from here to the next one, R prime, because these are sorted. So eventually the R can iterate n times and L iterate SQRT times for each query. So the overall length of the things that we're doing is n SQRT. Okay, if you didn't get it, it's not that important because there is implementation. But this is it. When you had some queries that you wanted to answer and you wanted to have a data structure that includes only the elements in this interval, and you wanted to do it in a good way, you can use more algorithm. So it would sort all of the queries. It's doing it offline. It would sort all of them, and it would give you the data structure once it has it, and you would answer the queries that were asked there. So more queries. So as you can see, it's sorting them like this, which is the exact thing that I said. This sorting is good. There are some other ways, Hilbert order and things like that, that they are also better than this, but this is already good and in security. So it would sort all of the queries, and then it would just move L and R until it fits the query. So just doing it easily. I mean, there is nothing special here. While L is greater, the point that you want to reach is greater than the point you already have, you just increase it and remove from the set. And it has add and delete. The most important part here is you should first do the adds and then deletes, because unless you may delete something that you already don't have details. Yeah. This is the whole thing.
Can you explain to me?
Okay.
Now lose that.
Let me see. I don't know what this is. I would say forget about this part because I never saw something like this, but I don't know. I don't know. Ask me later actually. Yep. Okay, finally the first one is finished. No, not it. SQRT. There are some other pieces of SQRT. I'm just giving you some ideas here. Not implementation. Once you wanted to implement it, you should do it by yourself. The thing is that, so for example, I guess I don't have any problem right now. You have some queries and you have some updates on some queries. This is asking queries to update. One of the tricks that you can do is so you have 1 to k. These are the queries, right? You can divide it into SQRT parts. SQRT of Q actually. But the thing you do is that you would have a buffer of the queries. Once the size of the buffer reach a security of Q, you would apply all of the queries and recalculate everything. So let's say that the query was adding to the L and R value X. Okay? This is a simple problem. So the queries are this, and they are asking for sum of something or things like that. Okay? The thing that I'm doing, these are the queries, is that whenever my buffer got the size of a security, I would go and apply all of this. How? I mean, you can add this when you have all of the queries and you want add all of them, it would be only a partial sum, right? So you would add all of this, and the order of it would be O(n). But because you're doing it at most security times, it's an security overall, so it's okay. So every time that the number of this is the buffer size actually, the number of queries in buffer reach the security, you will just initialize everything, redo the problem, and so once the query is asked, suppose that query was asked at this time. This is the query that you want to answer. Because the buffer was initialized here, all the queries up to here are applied. And you just go through all the queries in this thing, and you see, okay, you just do a lower bound. You see, okay, not lower bound. You just see if L or if the point that it's asking you is in this interval, you would add the contribution of that query to this. Simply, you are iterating over a QRT number of queries here again. So the overall complexity is NSQ. Did you get it?
I did that. I'm sorry.
No problem. So we have a buffer of queries, and the thing is that when you have the buffer of queries, when there is a query asking you here what is the sum, what is the value at P. So we are adding to range and asking the value at the points. Okay. The thing is that, so if you had a query like L, R, and X, if P is in this interval, you know to add X. Yeah. Okay. So if you just check a few queries before the ask query that you had, and check this, you can understand what is the contribution of this to that one. Okay. Now the trick comes in. You have a buffer of the queries that you want to check their contribution. Okay. Each time you would go through the buffer and calculate the contribution. But also, buffer gets empty sometimes. You're clearing the buffer sometimes. When the number of queries in it reach a sqrt of Q. And okay, when the number of queries in the buffer reach a sqrt of Q, you know that we want to add. We add to L plus X, we add to R plus 1. Minus X, this would be a partial sum, and we would recalculate the initial array 8 that we had. So, again.
And why SQRT?
Yeah. So this is the timeline, okay, of the queries. This is the time that the buffer had one query, buffer had two query, until the buffer had a security query. Okay. Here we cleared the buffer. Again, one query, two query, security. We cleared the query. So in the time that it's asking you this query here, you already know that the buffer got updated to this point. I mean, it has all the things already initialized in the array. And you just have to calculate the contribution of each query to the answer. I just iterate over them. The point is that the number of these is less than SQRT. Because if it was greater or equal to SQRT, it was actually the buffer was cleared. So it's less than SQRT, right? So for each one, we are iterating over less than SQRT. So here we have minus SQRT. Good. Also, how many times we clear the buffer? At most security times. Because the size of buffer should reach at least security, and
Yeah, it's divided by.
so security times we are doing the clearing buffer, and the clearing of buffer has an order of linear. So it's again. So we actually did a good trade-off in reach and security.
Okay.
This is one of the tricks.
Oh, this is the reason why you choose SQRT. It's a trade-off between
Yeah.
the
Yeah, exactly.
Okay.
Yeah. unless one of them would be heavier.
The easy is the what it's called the SQRT decomposition.
No, this is one of the
It's different, okay.
Now let's see what is the security component. You're in a class that if you ask something, you would get the answer. Okay, let's suppose that we have the same thing. Okay. Listen to me here. This is important. Now I'm dividing the array into blocks of SQRT. So that was timeline of queries, but this is array. This is different. Okay. So this is array M, array A. This is 1 to SQ. This is SQ plus 1 to 2 SQ, 3 SQ until N. The thing that we know that the length of each block is SQRT. Okay. Now let's suppose that let's do the problem that segment, the lazy segment we solved. Adding to the range, understanding the sum of the range. So the query is that LR X this is a query plus what is the sum of the okay, the thing is that okay. When you have a update query of L and R, it would be something like this. So let me sketch it there. Yeah, L and R. There are some blocks that they are totally, they are fully inside the interval. For these blocks, we just have a lazy, exactly, lazy of the interval, and we just plus equal to x. Because we know all of the elements in this interval have this difference, have this thing. This is equal for all of them, okay? And there would be exactly two intervals that they are partially intersecting with the L and R. For these ones, we just iterate over the numbers and update all of the lazy and the contribution that it had. Okay, so here we are iterating less than SQRT 2 times array. This is less than SQRT, and we are iterating over this. This is the first part. We are operating over this again, but it's less than SQRT. This is the second part. Okay, and now we are just iterating over blocks inside, not the elements. So how many blocks would be inside at what SQRT? Again, we would go and change the lazy of this, then change lazy of this. Okay. Once the other query was asked, let's say that the once they wanted you to answer what is the sum of L to R, the thing is that you would again have the blocks. So two of the blocks are intersecting partially, and all of the others in between are fully in it. Okay. You just iterate over this. You know the sum of them, which is sum before adding the queries, sum of I. And you know that the lazy of them is applied to all of them. So it's sum of I plus lazy of I multiplied by length of it, which is SQRT, but I would write Li, the length of the I block.
So we also store the initial sums.
Yeah. And we just have, we wouldn't update it, we just have the story there. And yeah, so for each block, which is fully inside, we just calculate this. We are iterating a square time, and we know the sum of these blocks. Pretty perfect. And for understanding the sum of these things, we just iterate over them, and some of them get some of them, and also the lazy and
Okay, but for all elements inside the two partial.
Yeah. So again, the iteration is less than SQRT. So the overall complexity is an SQRT. This is a SQRT decomposition because we decompose the array into SQRT blocks. And it's something different from the buffer SQRT trick that I told you.
Yeah.
Is that this is still working?
Yeah.
Are you still following?
Yeah.
Okay, these
So,
are. Yep.
did we finish the first part?
I think data
I mean,
structures. Yeah. Do you want a break?
okay. I mean, maybe we can go a little bit fast on things that are not that important because otherwise it's gonna take the whole day.
Yeah.
Because we spent 1.5 hours on the first part, which I mean, I think it's important, so it's
Yeah.
fine. But maybe
I
if there
think
are other,
this was the heaviest one actually. The other ones, I mean, also graph is large, but I mean, you already know what is DFS, PFS, Dijkstra. I don't have to cover them.
okay,
Yeah, but I go. Okay.
Now FFT.
Now FFT. Yeah. Okay. Polynomial, matrix, determinant, solve linear, and matrix inverse, FFT entity. The first four, they are just there. They are not the best order, I know, and they are not usually useful. And okay, this is the polynomial. You can see it later. Just to be faster, it's just saving the coefficients of the polynomials. Then this function finds the roots of the polynomial, real roots, not complex ones. This interpolates, so you can give it the coordinates and it would interpolate all of them into the polynomial of order n. The complex is n square. And let's skip this. Linear reference, skip this, yeah. We can also remove it. These are not useful. I don't know this even myself. So let's skip it. And then if you want, you can study it later. Hill climbing, I mean, these are not that useful. Integrate, adaptive, okay. Let's. Okay, yeah, all of these are the things related. This is solver. This would solve ax equal to b, but this is not something that we usually see in SWERC. I mean, if we see something like that, we don't need to solve the. Okay, let me explain this. For calculating the inverse, usually when we have problems in code forces, because we are not dealing with doubles, we are usually dealing with the natural numbers, and we have a problem with overflow. So when they want to check if your algorithm is okay or not, they would give you a modulo. They would give you a mode. So you are actually calculating everything in mode something. Okay? And this is the funny part because inverse of the matrix, we cannot calculate the inverse of matrix, but we can calculate inverse of matrix mode something. Why? Because a minus 1 exactly with the indeterminate theorem is a to p minus 2. So we are not usually interested in solving ax equal to b because we need everything modular and we just apply things like this and matrix multiplication and that's it. So these parts are not useful. Then matrices. This would calculate the determinant, I think, yeah. Another thing, not important. Solve linear, again, not important. Unless there's a Gaussian elimination, but that's too advanced and not even not in the notebook, so there are some problems with that, but forget about it. Again, this not important. Matrix inverse, this is again calculating the inverse, which you can see this is double, but again, we are not that interested in it. And these are some theory, not important. And here it comes the FFT. Okay, FFT. Really, this would be something that you need to know in SWERC. There would be one problem, maybe. So every 3 years there is one problem, something like that. So I think this year there would be maybe. But the things that you need to know is not the whole Fourier transform. You just need a few things. Uh, you have a function, and for this function, we have a polynomial of order n. you can either take the coefficients C1, C0, C1, Cn minus 1 to represent this thing, or either you can apply the FFT on it, the Fourier transform on it, and it will sample this thing in a specific points which has I2 pi divided by, if I'm this is right, right? And it will say the value of the function at this point, 0, 2. And this representation is good, and this is also and again, with having this sequence, you can identify the function again, the polynomial again. This is a good transform that you can do. But what is the point of doing it? The point is that let's suppose that you have two polynomials and you want to multiply these polynomials together and then get the value of polynomials on few points. Okay. If you want to do it with the coefficients of the polynomial, you have to calculate the new coefficients for the new polynomial, which would be n squared, right? But the thing that you can do is that you can do the sampling that I said. You can apply FFT on the thing. So you would have this, and you would apply. So let's suppose that you want to apply. This is C prime, and you are multiplying these two polynomials. Okay. Then you will apply FFT on both of them. So you would have x and also x prime. And the point is that now if you apply the FFT on both of them, multiplication is really easy because you just have to multiply these two values together. And it's just a simple linear multiplication. Okay? And you would have the answer. You would have the answer which I will y. Y0 until y. Okay? You would have this. And this is identifying the polynomial that you have. And you should apply inverse Fourier transform to get the actual function. Again, you apply FFT and you divide it by -1, something like that. Because if you apply FFT twice, you would get the same polynomial, but you should also multiply by coefficient. But again, this is also implemented here. Okay, so this is the whole idea behind FFT. And there are many problems that you can solve. I'm not an expert on it, but I mean, sometimes you can say that the answer to the problem is for example, you have this thing to power n, and the answer for the problem, the dpk, is exactly the k operation, the k coefficient of this polynomial. Yeah, and you would do the polynomial multiplication really easily. Also, power is really easy because again we have the same thing. We just have to do the multiplication by logarithmic. How would you?
With the binary formula, yeah.
Yeah. But I don't. What is the name of it? Yeah, binary separation. Yeah. And yeah, sometimes so you can solve some problems with this. It's useful in DPs. If I think this wouldn't be enough to solve the problem at SWERC because it wouldn't be easy, but maybe you can study a bit more, maybe 1 or 2 hours more by yourself. So maybe you can solve. Yeah, especially you because you already did the mathematics Olympiad. Yeah, and I think you would be able to solve that problem. Okay, but again, when you're doing FFT and Fourier transform, you're using complex numbers, and this is not again the best thing that we can do. So you are using real number doubled, it's a complex number. There is another thing. You can use entity, which is I think it's also mentioned here. Number theory transform. It's doing the same thing as FFT, but modulo something. So it's doing again everything just in another mode, and it's easier to do other stuff. Yeah, this is FFT and entity. I wouldn't go through it in more detail. Let's just see the implementation of entity, and then FFT is the same, but you have to do something with complex numbers and other things. Let me show you my implementation, this one. I don't know about this one, but let's see mine. Nice. So the implementation is exactly that. If you are doing the inverse, you would change it here, and if you want to do inverse, it would multiply by inverse of mxf, which is something there, which is a coefficient. Yeah, but you don't care. So you can apply entity like this. It would apply on the same function. It would save it on A again. That's why I'm passing the pointer. And if you wanted to do the inverse entity, you just change it to 1. That's it. Then I will also share this.
Will we update the notebook?
Yeah. You should update actually. If you know how to work with it, it would be really great. I can show you. Do you have GitHub?
Yeah.
Do you usually use GitHub? Okay, that's a need for them. That's a must. Okay, numericals. Then number theory. Modular arithmetic. We already know what is that. Mode power. We know. Mode inverse. I explained. Eratosthenes. So yeah, the thing that is implemented here, that you have the mode, you have a struct, and you have all the operators: plus, minus, multiply, divide by something, invert. What is this? GCD is equal to 1. Okay. Calculating the inverse. If the GCD is equal to 1 is in the same thing, not important. Power. Yeah, this is the implementation. You can use it later. Then inverse, again, here we are using the little Fermat theorem, and we are doing when mode is prime. And so here it's calculating the inverse of all numbers from 1 to the limit. I would say by mode. This is the thing that we saw in the logarithmic order. It would calculate the answer. Or maybe it's something different. No, it's the same. Mode like return something blah blah blah. Not important. Mode sum. Again, I think it's not important. I mean, this is mathematics and you can do it by yourself. And yeah, come on. This is also not important. I mean, you can use it, but the square t. Okay, Eratosthenes. First, I would explain a bit of number theory here. Let's go back to the theory ahead. So combinatorics. So let's cover binomial coefficients because we need the modulo inverse there. So for calculating the NCR, we know it's factorial of n inverse of the factorial of r multiplied by inverse of factorial n minus r. The thing is that this is my implementation, and I think it's easy for you to follow. The first two things, they're 1, and then I'm calculating the factorials. Then this is a good way. First, I would calculate the inverse of the last factorial. From that point on, to understand the inverse of I, you just have to multiply inverse of I plus 1 multiplied by I plus 1 and get that modulo mode. This is fast. And here you would pre-process F and I, and then when you wanted NCR, you just do this. This is the power in logarithmic order. Again, you already know this. This is the inverse. Because mode is prime, I'm using little Fermat theorem. Another thing. When n is really big, n could be up to 1 in I, but you know that r and n are close enough, so you can calculate the NCR by just iterating over the last r digits. I mean, because you know that NCR is because we know that NCR is n divided by n minus 1. It's r plus 1 divided by a factorial, right? So something like this. I wouldn't go on in details, but you can do it fast if n and r are close enough. Okay. Any question? No. Then Eratosthenes. So there is the algorithm of Eratosthenes that I think you already know to understand which to find the primes up to n. Again, let's see my implementation instead of this. But it should be the same. You can also change the implementations. Okay. Okay. I will also explain the factorization, prime factorization here. So this is the thing. We want to find all of the primes from 1 to n, but we want to also calculate something extra, which is LPF, least prime factor. Just why I call it LPF. I initialize with 0. Then from 2, we start. We do the Eratosthenes thing. And if we don't know the LPF of a prime of a number, that's a prime. This is the Eratosthenes, okay? So you would add it as a prime, and you would say LPF of I is I. This prime factor of I is I. That shows that the number is prime. And for that problem, for that number which is prime, you would also you would go through the let's say that's P. You go through P, 2P, 3P, go on, and you would set that number as least prime factor of that number if it's true. To implement that, I did this. I don't want to go in details, but it does it, and this is really optimized. At those days, I copied it from Tourist, and so you just run this, and you would get LPF for all of the numbers, and you would also have a PRM which calculates all of the primes. PT is the number of primes it found. Then for factorizing a number, the easiest thing you have to do is this. You just get the LPF. LPF is one of the prime factors. You just divide the number by LPF, the number of times it has the power in it, this while. And then you have all of the factorization. Maybe you want to do something related to the primes and things like that, but you would get the factorization like this. And the order of it is really good. I mean, it's better than log for sure, because I mean, we would have at most log n different primes, but it's really better because if you do the multiplication of 2, 3, 5, I mean, if you do the multiplication of first primes, you see that it's growing really fast. So for 1e5, I think it's 10. So if you multiply the first 10 primes, maybe 8, 7, something like that, you would reach 1e5. That's the thing. So the number of different primes that the number could have when we have an n in the problems, it's something like 7 and 8. Maybe I saw some problems that use that. Again, this is doing the same thing in the factorization, not important. And this is telling us it's getting a prime number, and it's telling us which is the order of it in the PRM list. Not important. But yeah, the most important part was this part. And also having the idea of LPF, because it would help a lot. Also in the last rounds, when I was talking with Gabriele, one of the problems was like this. I don't know if you remember it. No, maybe Pasquale would remember it. Yeah, there was one of the problems.
Yesterday's round?
No, it was D1. D1 plus D2 last week. Yeah, which you had to know the LPF of all the numbers. So. And okay, so where were we? Yeah, this is the same thing. This is the normal save. Read it later. The order of it is n log of log n, n log log n. Log This is not hacker, man. Don't be confused. This is this. This is really fast. Good. Uh, okay. This is a famous thing, but we also don't use it that much. It would somehow guess if a number is prime or not, and it works up to 7 would weight 10 to power 18, and the order of it is good, so some people use it. But I mean, we usually don't have that kind of problems to see if the number is prime or not, and we usually don't have these large primes because we would see a overflow if the prime is more than 10 to power 9 and we are getting something modulo that we will get overflow. And here we have the factorization, randomized solution. These things are good. I mean, maybe you would find a problem in SWERC that this appears, but yeah, just forget it for now. And if in the SWERC you saw a problem that you thought it would be useful, read it. And here, okay, so we know how to calculate GCD, but there's also another thing. What if we wanted the function to return the coefficients here to the GCD? Because we know that there's a linear combination of these two numbers giving the GCD. And exactly by doing the same thing, I mean, you can solve it saving the operations that you are doing in GCD. Again, read this. CRT is Chinese reminder theorem. This could be useful, but not that much. Just read it later if you want. But you know the reminder of the number with some modes, and then you can get the number in the login time. And Bezo is the thing that we are using for the GCD, and you can get the coefficients like that for this. And phi function here is a function that calculates phi of the numbers. Why phi is important? As I said, maybe sometime we want to understand the inverse of a number when we are getting modulo a non-prime mode, and then we should use the phi function of that mode. Yeah. Is everything clear up to now? Okay. Fractions. So sometimes you saw that solving a problem with double things, double elements wouldn't be good because it has really a large error. So in that case, you may use fractions. You may use the nominator, the pair of nominator and denominator, and you would represent all of the numbers like that. And the multiplication, everything would be easy. I mean, it's not that hard. And the thing is that when you have a fraction, you just divide both of the numerator and denominator by GCD of them. That's why they included here, but it was not that needed. And this is a simple multiplication of that. It's retaining pair of long. And if you are doing something like this, be careful with the overflow. The idea was more important than the implementation itself, but you can look at it later. I don't know what is this. Forget about it. Yeah, this fucking thing. Primes, estimates. I mean, these are some facts that they may be useful, but I won't go through them right now. So maybe in some hashings they would be important. I mean, there are some guess on how close are the primes and how to get a random prime and things like that. But yeah, I will give you a moment to read this part, and I will drink water. Okay. All right. Okay. Mobius. Uh, Mobius is useful, but it's not easy to tell you. This is the definition, and there would be you can implement it by yourself. And yeah, let me see. I don't know. If you wanted to read Mobius, read it later because I don't remember it really well right now. I would confuse you. I can write it here. Yeah, but I think it wouldn't appear in SWERC. Combinatoric. This is mostly theory, and I showed you how to calculate binomial coefficients. So, for example, dragment. This is a famous. These are famous problems. Dragment is number of permutations that none of the elements appears at the same position. So we don't have ai equal to I. What is the number of these permutations? This is a problem that dragment is solving it. Some of these numbers could be important during the competitions. So I remember that Catalan was appeared in last words. Yeah, and yeah, you may refer to these parts. This is also another thing. You can read here. Partition problem, yeah, for sure. It can appear, and this is not binomial. Okay. This I don't know what is it. Purple numbers. Bernoulli numbers. This is advanced. This is advanced, This is related to FFT. Just remember that you have this stuff in the notebook. Then Stelling numbers, the first kind and the second kind. These could be useful, yeah. Especially in combinatorics problems because they have a heavy theoretical side. So you may see something like these numbers. And you already have the information you need about them here, and you can even study them at SWERC. You can leave it there. Bell number, Catalan is really important. I would advise you to see Catalan because I think it may appear as a combinatorics problem this year. And just search what problems are solved with Catalan and what are the famous things. And for example, one of them is that you have a grid and you don't want to pass through the diagonal. What are the number of ways to go below the diagonal and reach the last element? And also some other things. This could be useful. I think they listed them here. Yeah, I think they listed them here. Subdiagonal monotone paths in n by n grid, a string with n pairs of parentheses. So number of valid parentheses strings is also Catalan. Binary trees with n plus 1 leaves. Ordered trees with n plus 1 vertices. Okay, I don't know. Ways a convex polygon with n plus 1 sides can be cut into triangles by connecting vertices with straight lines. Nice. And permutations of n with no three-term increase in subset. Yeah, this is also really beautiful. And they listed them here, so nothing to do for you. Okay. These are also some other things. Fragments, I said what is it? Expected value, I think you already know. Linearity of excitation, I think you already know. Stars and bars. Do you want me to explain what is stars and bars? Or you already know? You don't know? Okay. Maybe you know it, but with a different name. Okay, stars and bars. This is the thing. You have A1, A2, plus AN, and sum of them is equal to K. Oh, I know that. Yeah, and you want to know the number of ways that all of these are
adjusting in the English.
You also know it? Really? Yeah. Okay. Just to explain it fast, is that you put K balls. I mean, it's also called balls and balls. Also stars and bars. Okay. You put K of them, and you have to choose where to split this. So you're choosing these balls between these balls, and yeah, is the thing. So if you choose these, if you choose n-1 balls, you're actually saying that okay, the first one is 2, 2, 2. This is the same representation, and yeah, that's our goal. Okay. Graph, finally. DFS, we already know. DFS3, DFS, there are some facts that you should remember. You're using this, and this would unlock some skills for you. I mean, for example, in the DFS3, we may have package, but we don't have cross edge. You cannot have it like this. Okay? You know, I mean, all of the package are from a children to a parent. This is the fact in the DFS theory, right? Did you know that? All of the package are from an to the one of the ancestors, parents. Nodes, all of the vertices, all of the back edge. These are package. The edges which are outside the DFS3 are from a node to one of the ancestors. This is the fact that we have in DFS3, and it would be really good. DFS order. DFS order is also important. Listen carefully. So again, we have the tree. I'm just doing the DFS. So this is what DFS does. I can write numbers for it. Then I will go to 6, 7, 8, 9. Then I go back here and 10, 11, 12, and 13, 14. This is the DFS order. Okay, can you see it? Yeah. This is important. The values I put here is a starting time. I usually call them STM of the vertex. Okay, this is a starting time in the sense that okay. Also consider the end time, and you will understand why it's starting. The end time of this DFS is when you saw all of the vertices inside this subtree, which is the okay. So you started at 2 at the time 2, then 3, 4, 4, 4, 4, then 15, and at the time 15, you're going from this to the next one. So the FTM of this one is also so STM2, FTM15. This one STM13, FTM15. I don't know, this one STM is 4, FTM is 5, 6, 7, 8, 9, 10, 10. Okay. A starting time and finishing time. Why is it that important? Because there are some facts. I mean, if U is ancestor of V, suppose that the starting time of this is SU, this is EU, no, FU, okay. And this is SV and FU. The fact that we know is that this is true. The interval that this one has is totally included in the interval the others. So if you wanted to just check if one vertex is ancestor of the other one, you just have to know the starting and finishing time and just check the condition. And the starting and finishing time is really important. I don't know how to emphasize that, but let me turn on some. So the good thing is that when you have a starting time and finishing time, let's write a DFS order array, which is the array that we will see the nodes. So, I'm just writing 1 to 16 in this case because I didn't choose any name for the vertices, but I will write V1 to V60 or something. Okay, these are the names. I mean, these could be 3, 4, 5, 7. These are the labels of the nodes. Okay, and this is the DFS order of the tree. Okay, the thing is that for the node U, okay, what is the position of U in that order? Which is the index of U in that? No. So this is the DFS order. Okay, like that. And we have a vertex. And there are things. Okay, what is the position of the vertex U in that array? Certain time, certain. So this is the index. Okay. And also, so this is good. But another thing, they are telling me that we have a subtree rooted from U. What are these values inside this? They are all next to each other. Do you understand? And what are the indices of that?
Yeah.
Exactly. STM and FTM. A certain efficient time. This is an interval. So if you have the tree and you do the DFS order and you would calculate the DFS order, then all of the queries on subtrees would be an interval query. So you may have a segment tree question here just by calculating the thing. So if you had a problem that it was giving you some queries on the trees in the sense that okay, plus equal all of the elements here to x. So plus the subtree. It's an interval. If you do the DFS order, and you can do it with DFS, you can do it with segment tree or any other data structure that fits. This is an important thing. Okay. Also another thing. I mean, as your friend mentioned before, there is a. We know that LCA is exactly solving LCA is exactly equivalent to RQ. But why is that? Okay, I want to do a, we call it Euler tour of the tree, but I think it's not the right name. Instead of DFS order, the thing that I'm doing is this one. So each time that I'm seeing the vertex, I would again add it to the DFS order. So I'm not adding one vertex once. I'm adding it actually twice. I think. So let's say that this. Let me do it for that one. So it would be, I will start from 1, then I will go to 3, 4, 5. Then I'm going to parents. Again, 4, 6, 7, 8, 7, 9, 7, 6, 10. I think we got it. Yeah. This is the, we call it Euler, but it's not the right name. Sorry for that. If you calculate this for the tree, the thing is that whenever you wanted to understand the LCA of two nodes, you just have to look for the interval of them and just get two of the get the first appearance of the first one, the last appearance of the last one. You would have an interval. The vertex in that interval, which has the minimum height, is the LCA. Because why? Because while I was doing that, I was doing something like this, and I reached U. Okay, then this is V. For reaching V, I went up to. I mean, I did something, yeah, but I went up to LCA.
Yeah.
And then I came down. I didn't see any other vertex from above. So the one with the minimum height is the answer. So you can have that order, the Euler tour of the tree, and you just say the height of them, okay? And range minimum query would give you the LCA. That's why they are equivalent. Okay. That's a way to solve LCA question. Okay, I suppose all of you know what is LCA. No, LCA is the lowest common ancestor. And that's the way to solve LCA in O1 with RFQ. But we usually do it in O of logarithm to don't implement too much. But again, why I mentioned this, because as you can see, this is also related to starting time and finishing time somehow. So these things in trees are really powerful, and you can use them in tree problems. And starting finishing time is one of the most important. Okay. 13. Okay, while we are here about DFS and trees, let me also tell you another thing. Do you know how to calculate the diameter of tree, or should I explain it? You don't. Two DFS.
Yeah.
DFS tries. Yeah, exactly. So the thing is that for calculating the diameter of the tree, you just do the DFS or BFS for understanding the distance of all nodes. Once from one, so you take one as the root and you would do it, and then you would understand. Okay, this is D1, which is the point which has the most height for the sum. Okay, then again from D1 you do another DFS or BFS or anything, and then the one with the most height D2, this distance is diameter. The fact is that the important fact is that in the trees for each, so if you had a random vertex in the tree for each vertex is so the maximum distance from this one to one of the other vertices is the maximum distance of this with either of the diameter ends. So if you just say D1 and D2, if you know the diameter of the tree, but you knew the vertices, just for understanding what is the maximum distance that you have from you, you just have to calculate the distance from you to D1 and from you to D2, and the maximum of them is the answer. This is a really important fact. Many times it appears in many contests. Did you all get it? Okay. And for calculating the distance from U to V in a tree, what we do LCA. This is V, this is U. This is LCA that we calculate with the algorithm that I will show you. We get the height of this, height of U, plus height of V. We calculate this part twice, so we minus height of LCA twice. This would be only this path. Okay, this was also another important thing. Now let me say what is LCA. LCA is lowest common ancestor, as I said. The idea to solve it is binary lifting. If you don't know it, I cannot teach it really fast here. Read it by yourself. This is an important idea. It's also appeared in RMQ as you may guess, which is a sparse table. And let's see the LCA. Let's see. Okay. This is the binary lifting idea to calculate the LCA. So the memory is n log n. The time is also n log n. And here you have the LCA. This is the implementation. The implementation is good. I approve it. And yeah, okay, this is the LCA. Nothing more. And the other things. Okay, topological sort has SCC. We will do it afterwards. Let's start from BFS. So consider that you have a graph. For understanding the distances of the distances from a source, you can run BFS if all the edges have the weight equal to 1. Okay. Also another thing, if all of the edges have the weight 0 or 1, we call it BFS point. So BFS 0, 1. It's also doable by BFS. So you had the BFS, you had the Q that you were appending at the end. It was the fact you were using. If the weight of the edge was 0, just append it to the front instead of the end. So instead of push back, you do push front. Just for your information. But generally, if the weight of the edge could be up to 10 to power 9, you have to do Dijkstra, which you use PoliTO and things like that. Dijkstra, if you know the idea behind it, is kind of DP. You can understand. So many times they apply some DP or something on the Dijkstra. So have it in mind. And also, if the weights of the edge of the graph that we wanted to find the shortest path in is up to n, you can also again do it with BFS. But this is BFS with levels. The thing you do is that for each weight, you would have a vector and you would see the edge. So when you are relaxing one node, instead of using the priority queue, because you already have all the things in the levels, you just push back the updated, the relaxed. So you have a relaxed vertex that's updating some of the distances of one of the vertexes next to it, which is connected by the edge. Okay. Instead of adding the other edge to the priority queue, which is sorting them by the distance, you would have a vector of size n that for each level you know what are the values and you just add them there. I think none of you got it, no problem. But there is also something with that. Yeah.
Useful. Like, should we use it instead of dice, right?
No, do the extra. No, yeah, sometimes it is.
Okay.
So yeah. Starting and finishing time, LCI binary rifting, okay, good. SCC, HL, okay, let me start with Bellman Ford and Floyd Marshall. So whenever Bellman Ford and Floyd Marshall. This is the problem that they are solving, but they are all solving the problem in order of n3 or nm, which could be n3. This is n3, this is nm. So Bellman Ford is nm, this is n3. And it's what's the problem? The problem is that we want to know the shortest path for each pair in the graph. So for each pair of the vertices, we want to know what is the distance of them. And we want to calculate it once. I mean, you may get confused that, okay, we had LC, but LC is solving that for trees, not for the graphs, not for the general graphs. So if you have a general graph and you want to know the distance from each vertex to other vertex, you have to do n square at least, I mean, n cube eventually. You apply one of these. These are really easy and you can apply and you get the distances. I think this is enough. Okay, topological sort, and yeah, let's do topological sort and SCC. So now again, the game is different. Now you have a directed graph. Okay, what is DAG? DAG is a directed graph that doesn't have any cycle. So you don't have any cycle. So you can see the DAG. You can sort the DAG. You put the source here, and you put the sink at the end. And you can sort it in some way that all of the edges are from left to right. This is the definition of topological sort of the DAG. Okay, so the problem is that you have a graph and you want to do the topological sort. With DFS, they can do something. I mean, it's just a normal DFS. But on the if you, how would you say that, the reverse edge or something like that. So whenever you wanted to put this thing, you would do a DFS, but on the reverse edge. So you know, okay, so I should put this one before that. So let's do this first. Then you would do the DFS. I mean, this, you see, okay, so let's put source first, and then you would create the topological sort. It's only a DFS, as you can see. They are stupid because they did it n log n. No, it's not n log n. It's cube, priority cube. Okay, but they did it something. I think it's something like BFS, but you can also do it with DFS. I can show it later. So this is the general idea. You can get the topological sort. Okay, but what if the graph is not acyclic? So it can have some cycles. The thing is that there's a definition of strongly connected components, which means that you have a connected component, you have some vertices, that from each one you can reach the other one in both directions. So there's a path from this one to that one and also from that one to this one. And this is the strongly connected component. So let's suppose that we have a general directed graph. We can decompose it into some different components which are strongly connected, and each one is maximized. Each one is maximal. Okay, and from now on, so this would be the first component, second component,
Is that called Araujo algebra?
Yeah.
Ah.
Then, so these are the connected components, strongly connected components. The thing is that if you then see each of these as a node, this is the G prime that I'm creating. This is a diagonal because you don't have any cycle. Because if we had a cycle here, we could merge all of these together here. These were not maximum products. Yeah. So the idea is exactly that. You calculate the SCCs in the general derivative graph, and there would be some fact for the SCC because you know that each pair is accessible by a path to the other one. You can go through it, and you would have a drag, and there would be something to do with the topological sort, and then doing some. So it may appear in some details. Let's say you calculate SCC, certain component, and then it would sort the SCC with the topological sort, and then you would do the thing you want to do with the dynamic programming. And yeah, this is topological sort and SCC. Let's see the code. Just a second, I can't find it. Okay. This is the part doing the DFS. Okay, this is SCC. You just call this. This is the graph, I mean the vectors. The adjacency matrix somehow, but it's not full. And what is F? I don't get what is F. I think it's a function. I think you can leave it in. I don't know. Yeah, but I can share also this implementation with you. And we can substitute it. And okay. What else? What else? HLD. Okay, let
We take a break for HLD. Maybe.
right now. If you want
Should we
to.
take a break now?
Okay, yeah. How many minutes? Maybe 5. Okay. Okay, 5 minutes break. Oh.
Hard talk.
Yeah.
With all those all shouldn't be anchored.
Like that.
It's all the it's even more. I mean, it's so for sure. If I mean, for a lot of things you said, okay, this is not important. You will need this. Okay, so if I like Yeah, maybe those things. Maybe those things, yes, but the FFT part, maybe those, yeah.
Actually, I wanted also to say these things. I mentioned island connectivity, centroid decomposition. This is beautiful. But
Yeah, centroid, it's one of the problems we talk about in class.
Yeah. No, but it's not just centroid. It's centroid decomposition.
Oh,
Yeah,
decomposition.
yeah, it's another thing.
But do you know like 50% of those, all those things? No,
Just 50%. I don't think so. Until LCA, yes. The first thing until LCA. Do you know HLD? HLD, you know? No. What means HLD? Heavy decomposition. Heavy light decomposition.
How do you know those things and are specialists? Like it's impossible.
I didn't do so much importance and the importance of oil tests in high school, I would say.
Oh, nice. So you participated in Olympics in high school?
Yeah.
In Turkey?
Yeah.
Did you get medal?
No.
Okay, no problem.
Because last year it was a little unlucky for me. The contest management system was trash.
Like meta. Yeah. Like the meta account. Yeah. Yeah, that's quite fun.
I probably look there.
Yeah, probably if you know all those things and you're not grandmaster, it's not for you because you are great also in math. But maybe the problem is math.
Maybe.
Yeah.
Maybe my math is not.
Math is more important than those things.
Yeah, in the contest.
Yeah.
But in SWERC, no.
In SWERC, no, it's because it's more about theory and the standard. But yeah, in contest, it's
Yeah, but I mean, I enjoy knowing this, even though if I was even expert.
Yeah. Or specialist.
I mean, your maximum rating is.
Yeah, my maximum rating could be also be grandmaster, but I'm specialist, so it's fine. Quindi le interview tu sei
Giovedì
Giovedì c'è
la
la
finale di Amazon. Poi ho fatto una l'altro ieri e l'ho passata.
E
con Amazon.
cioè, cosa fate? Tutta roba tecnica?
Il giovedì è stata tutta tecnica, ho fatto domande di SQL e Python, ma in realtà era facile.
Ok.
Non riesco. Il giovedì sono 2 consecutive, dalle 10 alle 12. Ancora tecnica behavioral.
Ma è Natale, sì, non devi essere pazzo.
No, vabbè, vogliono solo no, ci vengono parecchio.
Lo so.
Want to do this in the one session?
Esattamente.
Yeah.
I mean, we don't have much more time. That's the problem.
Are we beyond?
Okay.
No.
Dynamic programming,
Okay.
No, I mean, some of them are not important.
The easy graph, we have the hard stuff now.
No, come on, we need FFT and like that.
We are the hard useful stuff.
I think we are something like 7%.
E poi vabbè,
secondo me sì, I mean,
So è così che va.
it's better than nothing. Maybe we can do it more next year. But I mean, it's the first time that we have these good students, you know. Other time, the people who are attending, they don't much. And it's not a good thing to expect them. It's good to have a bit short. I mean, I see that you are understanding this.
Yeah, it's just
Sì, ma cioè,
Yeah. But the good thing is that we have the notes.
Pensavo studiassi più la...
No, cioè, veramente ci conoscono come loro. Infatti sono perché non è
Quindi da quello che adesso magari la o alla fine, ma considera che dove cioè,
Which means only short.
se va bene ti allunga un po'. Questo quale invece è tutto. Ok, ma sto proprio preso. Cioè, proprio preso. Il calò per vedere. Ah, sì. Ah, non è c'è in Spagna. Non in Spagna, era no. No, perché cioè, quello che che il numero che non ho mai lavorato lui vuole bellissimo, vabbè, quello che però comunque perché lei cambia le molti da fare il keyboard. Bring your requested because you're, I think you're faster, right? And I can with the Italian and American. That's it. Io volevo fare un altro. Invece no, for the keywords in the contest. We will be allowed to bring another or just replace. You are able to bring another. Let's see. So we have a US one. I don't know if your regulation space. Ah, okay. You can bring that. The wrong key. Bring us what? They are not allowed to use the previous provided. Well, okay. Yeah, and you should contact them in advance. Non-violence. Okay, guys, let's start. We have a mess. Vediamo. Pasquale and Mattia, are you here?
Yeah.
Okay. Okay. So, where were we? Yeah, HLD. But let me say something before that. There's also another thing by connected components. Let me just show you some pictures. So, int components. Okay, this is the thing. So, each component, you have a normal graph, and each component, each two vertices have two paths, have different paths. So the thing is that you have a component, and you can remove any edge, and still that component should stay connected. Okay, so they are two connected, something like that. And if you consider those components, sometimes it's really good because you can do something. And sometimes we apply it on trees, like this picture. I mean, this is one component, this is one component. You know what I mean? None of them are two connected components, okay? Because it's a tree. If you remove one edge, they are disconnected. But you have some back edges. So you have some edges that actually create the BCCs. So that's how they. So you have a general graph, and you want to understand what are the BCCs. You run a DFS, so you know all of the edges outside the tree are back edge. Then you construct the components. So there would be some components, and if you consider each of them as a node, it would be 3. But not that important. If you already knew it, it would be good, but not that important. HLD, okay. HLD. Again, I should. Okay, this is the HLD. So this is useful, but I'm not sure if it would appear in. Sorry, but this is the. Let me explain on that. So consider that we want to color the graph, and each color should be one path. I mean, if you look on the first color, there should be one path. So all of the edges in that thing have at most degree 2. Why should we do that? Because if we can decompose the tree into some paths, and we can do the queries, instead of having the queries in the tree, you can have the queries in the intervals again. So you write down the paths that you had in the trees next to each other, and then once somebody asks a question, if the ask a pair of them, if the pair is in one of those paths, you already can do the segment tree. I mean, suppose that they gave you and one of the ancestors, v, and they want you to say what is the maximum number between these two. So in this path, what is the maximum number? What is the maximum weight of the age, or something like that? Okay, and you want to solve something like that. You can decompose the tree in a good way in some different paths that's like this coloring. And for example, let's suppose that they asked 2 and 23, and they asked us what is the maximum number. So the thing is that we get all the colors that appeared in the path from 2 to the root, from 2 to 23, and we say, okay, one of them is green, one of them is red, one of them is blue, and we for the blue one, we see what is the intersection, which part of the blue we are interested, and for knowing the maximum of that range, this is only segment tree. I mean, this is only a data structure that you would use. So log n here, log n for red, log n for the green. Okay, until here everything fine, and we don't have any specific idea. The idea comes here. The ways that we construct the paths. The way that we do it is like this. So consider that we want to color the graph. First, we color all of the subtrees. So you have the root, like 23 here. Then you will color all of these childs, the subtree childs, and you have this. Then you have to decide which of these paths would come up, would continue until the root. Only one of them would do this. I mean, if you had this, you would see, okay, here we have one candidate, which is the green path. Another candidate is cyan path, blue path, I don't know. The yellow path and the red path. And you should decide, okay, which one should have the root in that path, where to put root, which path we should put it. The answer is, okay, put it with the consider the children that has the maximum number of edges, okay, maximum number of vertices, the heaviest, again, like the thing that we were doing in DSU. So this subtree has more vertices than the others. So we continue the path of that root to here. Why do we this? Again, because each time that, so consider this edge, each time that you need to pass from this edge, you know that the size of subtree is at least multiplied by 2. So how many times you would change the color of the path? Log n. So how many times the color is changed from a random vertex to the root? At most log n. Okay? So you will have at most log n different colors that you have to apply the query on it. Okay? And cost of applying one query on one path is log n. So overall complexity, log n multiplied by log n, log 2. And you solve the query really fast. Did you get it? Kind of. Should I explain the part in question?
Attach a subtree depending on the height or depending
The size. Yeah. So we know that the size of the, so for example, for these ones, if there was one vertex which was asked in the query, and we had to change the color, we are sure that the size of subtree is multiplied by 2. So each time that we are changing the color when going from this to the root, each time that the color is changing, the subtree is multiplied by 2, so at most log n times. This is the whole fact. This is the whole idea. So we decompose the tree into some paths, and we put these paths next to each other. The order is not important. We do a data structure like Fenwick tree, segment tree, or anything, RMQ maybe. And then you have the decomposition of the path from you to ancestor into at most log n colors, and you would have everything. This is heavy light decomposition, or HLD. Let's look for it in the notebook. I cannot see it. What is mentioned here? Okay. And black. This is the thing. So the first here is the part that it would decide what is the colors. I mean, no, this is just calculating the size of subtrees. Then here it's calculating the colors, if it's HLD. And it's calling only this for the biggest child, as you can see. Okay. And so it's decomposing the paths, and you can run the query. Query path, I mean, it's just doing the iteration and sees when the thing is changed. Let me see. Okay, modify path. You are adding to the path from U to V, okay? The value val, okay? Query path. You are asking from node U to node V the query that you have, which here is the maximum of the numbers or something like that. Okay, and it's applying the data structure on it. Okay, and what is this data structure? I think it's referencing to the actual segment tree. Yeah, because you see node here, right? This is the same thing here. The struct node, which was the lazy segment tree. So it actually used the segment tree and it applied in the implementation of the HLD. So I think you would be able, if you solve the problem with HLD, I think you would be able to understand what it did and implement it, I mean, to see what you need to do, okay? And if you were not able to do that, I think you are also able to implement it by yourself, because it's not hard to implement it, right? If you do it once, okay. This is HLD. Then flow.
You put a segment tree on every path.
Yeah. But I mean, don't do it for each path. Just put them next to each other. The order is not important. And run the segment tree on the whole thing. Did you get it? I mean, this is not the exact implementation it did. You have the paths, right?
Yeah.
Put paths next to each other in any order. It doesn't important. It's not important. And do the segment tree. You can ask the queries here, but they are not useful. And you're not asking. You're asking queries inside the components. But it's easier to build a segment tree once instead of building a segment tree for each path. And it's more efficient. HLD, link cut tree, it's something not important.
Tedesco poi, no?
Forget about it. MST is minimum spanning tree, which is solvable by DSU. I think Julio doesn't
Tem uma
know that.
nova
Okay, the thing
programa
is
na
that
qual
you
estamos
have
por enquanto.
a weighted
Então.
graph that you want to understand what is the minimum spanning tree. The thing you do is you sort all the edges based on the weight from the smallest one to the largest one, and each time you try to connect these edges. If it was connecting two different components, that's actually in the MST. That should be in the minimum spanning tree. If when you wanted to add the edge, they were already connected. Okay. Here we have directed MST, which is another version, not important. And okay, this is something good. Number of spanning trees, number of trees. There are some formulas you can read later. But where did it write the formula? I don't know. But there is a formula for number of trees. Not important.
It's just the proof of code one.
Yeah. What else? We covered these. Flow, matching, to set. Okay. Let's start from flow. Okay. Okay, I will give you the general idea on what is the flow. Then I will say what is matching and why they are related. And the rest is the implementation. The flow is that you have a directed graph. I don't know if it's a scientific format. Just a second. I think it's a cycle. Maybe it doesn't make any difference. I don't remember. But okay, you have a graph. And the thing is that this is the graph. This is the source. This is the sink. Let's suppose that this is the dike and it doesn't have any cycle. And each edge has a capacitor. It's C1, C2, C3, C4, C5, C6, C7, C8, 9. The thing is that you have a water tank here, includes water, and these are pipes. And this is the maximum capacity in the sense of liters that can pass through this pipe. 1 second or something. And you want to know if you plug this and wait enough, what would be the flow coming out from the sink? Okay. So this is the general problem that it's solving, and it solves in some way. But the thing is that consider that you divided all of the vertices in two components, which this one has the source and this one has the sink. And consider all of the edges here. And capital C is sum of the sum of them. We know that the flow coming out from the sink is not more than C, right? Because it couldn't pass from this. So how would it be there? This is exactly the thing. Minimum cut is another problem, like maximum flow. So this was the maximum flow problem. The minimum cut is what would be the minimum C? What is the, if we divide the graph into two parts, what is the minimum sum of the weights of these edges in between? And you can see that the max flow is exactly the min cut. Exactly min cut. So you may see one of these, you may use one of these visions. And yeah, so max flow is min cut, and there's a way to solve it. Okay. The implementation is not important, to be honest. And I don't know what it does, to be honest. So I don't know neither. And okay, this is another thing. This is minimum cost max flow. Okay, it's also solving a more general thing. If cost can be negative or something, So each pipe had the flow on it, I mean, had the capacity and also the cost. So we knew that if 1 liter passes from here, it costs for us, let's say S1. S4, okay, S4. If 2 liters, it will be 2 multiplied by S4. Something like this. And it would give you the minimum cost max flow. So you have the max flow initially, then when you know that this is the flow coming out of sink, what is the minimum cost of having that flow? This is also solving that. And these things are really strong. Why? Let's think about another problem. Bipartite match. So you have a bipartite graph, and there are some edges. You want to know what is the matching, maximum matching. Matching is, so you are matching this with this, then this with this with this, I don't know, this with this. The thing is that these things, they don't have any vertex in common. These edges don't have any vertex in common. What is the maximum matching? This is a famous problem. For example, I mean, let's think that we have some gentlemen and some ladies here, and they want to marry each other, and the age just shows which one like which one, and you want to match them in some way to have the most number of them matched together, something like that. Okay, this is the matching problem, and there are some algorithms to solve them in different orders that you can also find them in the notebook. But I'm not satisfied with the implementation, so I may implement it and share it with you. And the order of them, but you can see the order of them. So matching. This is the first one, which is SQRT of n multiplied by m. So it could be n SQRT of n if it's really large. And this is the most used one. There is also another one which is easier to understand, and I can explain, but not now, which is nm, of order nm. Then, so also another thing. Maximum matching means minimum vertex cover. Why? So let's suppose that we had the matching. We had the maximum matching. So this is the maximum matching. So the size of it is max match. Okay. And the rest of the vertices. The thing is that we don't have any edge between these vertices. Okay. Because if we had one, we could add it to the maximum matching. So this set is an independent set. Okay. And there are some relation, which is the conic theorem. So let me show you the conic theorem. The minimum vectors cover so why it's not how should I say that? Okay, let me think because I don't remember it. But okay, this is one of the factors. So this is independence. And what is the problem that we want to relate to this one? The other one is, so we know the maximum matching, and the other problem is minimum vertex cover, which means that minimum number of vertices, that you know that all the other vertices have at least one edge to one of these. So you want to take minimum number of vertices, so you are sure. For each vertex, you either took it or it has one edge to one of the vertices you took. Okay. Okay, so at least one endpoint for every edge of the graph. And I don't remember the conic proof, to be honest. But the thing is that maximum match is equal to minimum vector vertex cover. There is a way to choose some of these. So, for example, choosing this, 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 and when you are choosing these, I mean, you are not choosing the same vertex of the matching. So you're sure all of the edges here are rotated. Okay. And because there is no edge here, you can prove that you can construct it in some way that also these edges are covered. I mean, they are at least connected to one of these. I don't remember exactly. Yeah, but minimum minimum vertex cover is maximum match. This is conic theorem. Last year in SWERC there was one problem which was solvable with this. Okay, okay, what's the relation between max flow and max flow? The thing is that let's just do the simple one. That you have the graph here, and you want to know what is the maximum match. Okay, you just set the capacity of each edge to 1. Okay, and you would have a source. You would connect it to all of these. This is a source C, and this is C. Is this the thing? I want to find something. I want to say that the maximum flow going out from the sink is exactly the maximum matching. Yeah, I think we can say that. How? Because we put the capacity of all of these edges into infinity. Okay, and we knew that maximum flow is the minimum cut, right? We know that none of these edges would be in the minimum cut because it's infinity. So all of the edges that could appear in the minimum cut are these ones. So I mean the two components are exactly these ones, but the thing is that we want to understand what is the maybe it's not the full thing, no? I want to say the minimum cut is the matching appearing there. I don't remember it exactly, sorry.
I mean, is the source giving 1 every time?
Okay.
And then you have max flow is giving us keeps.
Maybe.
If the source is outputting 1 and well, the sink is getting 1, the max flow is the matching, right? Because you're maximizing the phase.
Yeah. So I think so.
This is how AI optimizes my schedule.
This meeting got
Shit. Okay, then that's.
In this screencast, I want to illustrate how to use graphs. So remember what a bipartite graph is. It's a graph whose vertices could be partitioned into two distinct sets so that every edge connects to the
That's
vertex.
impossible. Okay. But why?
If you have 1 above, 1 below,
No, I mean by myself.
unless
Okay. No. Okay. Now it's fun. Okay. But how to prove it? I don't know neither. Okay. This is an exercise for you to do at home. And yeah, it's trivial. Then the other things. Two sets. Fourier tour technique, link cut tree. Link cut tree, forget about it. Central decomposition, we don't say that. This would be good, maybe at the end. I mean, we are almost at the end, but two sets also, I wouldn't say that. Maybe. I think the most important parts are covered. We will get back to graphs if we had time. Okay, dynamic programming. The most important things. So I think you already know how to do the iterative dynamic programming and memoization. And okay, so let's forget about that part. LCS and LIS. Do you all know what is LCS and LIS? Longest common substring and longest increasing subsequence. No? Okay. LCS. For LCS, you are given two strings S and T, and you want to know what is the maximum longest common subsequence, right?
Yeah.
You want to know what is the maximum length of the subsequence which is common between these two, like A, B, C, D, A, B, C, D, and okay. To solve it, you can do a N2 DP I and J means if you have I and J, then you have only the prefix here and only the prefix here. And for doing the matching, you just check if these two are equal, you get the maximum of DPI minus 1, J minus 1 plus 1. If not, if they are not equal, I mean, you can write DPI and J is equal to max of these things that I write. DP of I minus 1, J, not matching the first one above. DPI, J minus 1, not matching the one below. And if let's write J, DP, I minus 1, J minus 1. If these two are equal, we match them and we go both of them once. This is the solution. I think the implementation is already.
So it's n squared.
Okay, maybe not. LCS is not there, but you can implement it. Come on. LIS. What's LIS? You have a array of size n with some elements inside it, and you want to know what is the longest increasing subsequence. Okay. So like this. And, to do it, there is a famous DP thing that if you don't know, please study it because it's useful. Last year it was also there. I mean, last year there was problem which was solvable with LIS. So this is the thing. It does a binary search for updating TP. Okay, and this is LIS, and the problem is solved. Knapsack. Do you know what is knapsack? No. Okay, no problem. The thing is that you have some bags. The I bag has the weight equal to I, and the value equal to VI. W and VI. Okay, and you have a backpack which has capacity of C, so you cannot have the weight, some of the weights more than that. And you want to know what is the maximum value that you can get by putting some of these things inside the bag. Okay, there is a knapsack solution. There are different orders, but I think dp of I and c, meaning that if you only consider the elements 1 to I, first element to the I element, and your capacity is C, the remaining capacity is C, what would be the answer? For updating it, you just decide whether to put this one or not. If you are putting, it will be dpi minus 1 C minus wi plus pi. If you are not putting it, it will be dpi minus 1 and C. This is a famous thing. There are some other combinations of it that you can see here. Where is knapsack? Okay, fast knapsack. And it described what it's doing. So this is the thing this is solving the exact problem that I told you. But yeah, okay, fast knapsack. This is the only one that we have. This is solving the problem that I told you. There are some other combinations like, let's suppose the value of them is all equal to 1. So you want to maximize the number of items that you are taking. Okay. Maybe I think it's the same solution. I mean, you can do the same. Nobody cares. The other one is, okay, we have C. We don't have any value. Values are not important. We have only weights. Okay. You want to know if it's possible to put some of the item into bag. That bag would be full. So the sum of the weights would be exactly C. So you're not maximizing anything. And for that case, the answer is 0 or 1. Okay. So for each dpi and C is Boolean. Okay. And you can do it again the same thing. Okay. But there is a faster way to do it with bit set. Okay. If you wanted, you can also study this. Bit set is simply it is a structure. I mean, if you define Boolean, what is the memory of the Boolean? 1 byte. But 1 byte only for 1 bit, it's stupid. The thing that bit set does is it gets some integers, and using the bits of those integers, it would give you the Boolean values. And you can see that it's more optimized because of it. It's really faster. And it's easy to work, but you should search it on STL. I will just search it for now. So the other time that you wanted to see the recording, you would remember to search it. You would go there and study a bit of bitset. Not super essential. I mean, it's optimization. Then yeah, this is knapsack. Bit mask. Okay, let's say different story. So the thing is that, for example, I mean, let's say that you want to you have some elements which have value on elements, but it is up to 20 that have value on. Okay, and you want the values could be negative or positive or anything. I mean, this is a stupid question, but again, no problem. Maybe you want to know maximum XOR. Okay, yeah, maximum XOR. This is this. Yeah, maximum XOR. To understand, you want to find the subset with the maximum XOR. To do it, at least now I don't have any idea other than brute forcing, checking all the 2 to power 20 things. Okay? Sometimes it is something like that you do DP mask. What is mask? Mask is exactly a mask of bits. I mean, for the bits, for this thing, we are mapping it to the actual value it has in the base of 10. And because n is up to 20, the values would be up to 10 to power 6, so we are fine with the memory. Okay? And we calculate dp of mask, and it would be, I mean, you can fix a bit to see if it would be inside or not. If it was either inside or outside, you can refer to dp of mask minus 2 to power bit and update everything. So you just start the iteration from 0 and you go to up to 2 to power n minus 1 and calculate dp of mask. There are some complicated questions that could be solved with this. So this is one way to define your dp. if you solve one or two problems with that, I think you would get a full grasp on it. Okay. If you with math, you can study it. Also another thing. Let's say so. In this specific problem, because we had the subsequence, for each element there were two cases. Either it was in the set that we are getting the XOR, or it was not. Okay, but there may be some other questions that you have to decide for each element. Either it's in this A set or B, or it's not anywhere. So you have three things. So what are the possibilities? 3 to power n. But if you just implement it with bit mask naively, you would the thing that you need to do is that let's say find a mask for that includes both of them, then another mask that tells us which ones are in A. So first we want to know which ones are present. Then we will answer which one are on A. If we do it naively, you have to iterate over mask here 2 to power n, and then another mask 2 to power n. So you implemented it 4 to power n with 2 4s. And you are just seeing if it's valid or not. But it's not the best way to do that. There is an actual way to iterate over sub-masks, meaning that the mask is sub-mask of another thing, in an efficient way. Let's see if it's in the notebook. Yep. This is the thing. So if you wanted only to iterate over them. Yeah. You may not understand why it works. Yeah. Don't look at it. And okay, what else? DPL this is a common thing. Just okay. Sometimes it's important to define your DP, right? Sometimes you are working with intervals, okay? And because of that, you may think of DPL, meaning that you are solving the whole problem, but you're solving only for the interval from L to R, and that would help you to find the actual solution. I don't know. For example, you are at each step you are dividing the intervals into two to get the maximum, multiplied by maximum, something like that. And finally, you will see that you need the DP of L and R. Just have in mind that DPR is something common. I don't know how. If you wanted, I can give you some problems afterwards. Basic optimization tricks. Okay, these are just advice. So whenever you had DP and the order was not fine, I mean, whenever you saw a DP problem, I think all of you would be able to solve it with the DP which is not good enough. Maybe it has 1n more than the required complexity, or 2n's more than that, or something like that. And you have to optimize your DP. It happens. The tricks to do that. Look at your DP. Most of the time, there is a partial sum or something of that DP helping you to calculate things faster. Or just print the first few rows of your DP, and you would see some patterns, some maybe partial sums. You would see how the next row is updated from the last row, and you may optimize something there. So whenever you didn't know how to optimize it, think about partial sums, think about things like that, and also print the first rows. Maybe you would find a pattern. And generally, there are some problems that you would see patterns not last year, but there was a problem that we were doing in the SWERC competition, SWERC simulation 2018, if I'm not wrong. And it was Catalan, and we guessed it's Catalan only by printing it. You know? So yeah, also use that. There are some advanced optimization tricks that I wouldn't mention. And okay, DP can be merged with other things. As I said, Dijkstra. You may solve a DP FFT problem. You may use FFT in a DP problem. You may define your DP on the tree. meaning that you're solving only for the subtree. So dp of u means that you're solving the whole problem of the subtree starting from u. And you can update it from the children because you know how to solve for children because they are calculated recursively, and then you have to merge the children with the parent. If you do that, you have the dp on the tree. dp up and down, okay, nothing about it. But dp is segmenting. Maybe sometimes when you want to update your dp, you want to know maximum of a range, which is not very well defined. Maybe you can apply segmentry to understand the maximum, update your dp very faster, something like that. And dp with the matrix. So sometimes if it's not that the constraints are really low, I mean the dimension of the dp that you have is really low. So let's suppose that we have a dp. Okay, dp. What is dp? dp is a vector, right? It's a vector with size n, usually. Okay, dpi, the simplest one. Okay, if you know how to update dp from itself, so let's say we have the two-dimensional dp. Let me know that for each row, dpi is updated from only from dpi minus 1 and j, some j prime. Okay? If you know the transition from dpi minus 1 to dpj, you know how the update works. You just put dpi, this is dpi. And this is the fixed dp update. This is a matrix n, which gives us what is the updates. I mean, it's just a summation or something. Maybe it would be maximum or minimum. And because we know that if we multiply n by dp, if we multiply n by dpi minus 1, we would get dp of I. So eventually for getting dp of k, we just have to multiply dp by m to power k minus 1. Something like that, okay? And this is matrix multiplication. Again, we have the other things that we had, an m to k minus 1. We can solve it with dimension with d3, the dimension of the matrices we had, maybe n here. N3 log of k. This is also something that most probably would appear in this SWERC.
Is it like for Fibonacci?
We can also do it for Fibonacci. Yeah. You would need only a 2 by 2 matrix.
Yeah.
Because Fibonacci only uses the last two elements. Yeah. This is the Fibonacci. So this is the base of dp. This is the updates that Fibonacci does. So for getting the nth element, you just make the 2 power n. Yeah. So these were the things that I want to say about dynamic programming, geometry. Okay. I think you all know what is convex hull. Okay. The definition. So let's go directly. Let's go directly.
What's the convex hull? Like,
Okay.
is it some point? I know it's some points in this shape, but why?
Yeah. So you have some points. You want to find the polygon that has all of these points inside it, but it's minimal. When it's minimal, the vertices of the polynomial are exactly one of those points.
Okay.
Yeah, that's the convex hull, and it's convex in the sense.
It's convex in the convex.
Yeah. And so geometry. This is the geometry thing. In geometry, we have this thing here. So you have, let me zoom. Which you have a definition of points. This t could be double or integer, meaning that the coordinates are in double or integer. Okay. Then you have the operators for comparing them. This is Boolean, so they're comparing. This is just defining the points. You can add together the points. You can minus, multiply, anything. You can do dot product, inner product. You can do cross product. Definition of cross product. You can do cross products on the two vectors, and you can get these two. This two is just the norm to power 2. This is norm. You can get the angle to the. I mean, if you want to do the representation in angle and the distance from the thing, you can use this and other things. Yeah, here. Then you have some functions line distance. So you have the line. It's all defined here. I think you have AB, and you want to know what is the distance of point P from the line A to B. Just a second. No.
Is the
Segment distance.
will be printed out?
Hmm?
Will we have during SWERC? Do we have a physical copy of the booklet?
Yeah, you have to print it. Yeah.
So we
cannot
actually
copy it.
copy the code.
Yeah, unfortunately. We have segment distance. This is also one famous problem. I mean, there are many famous problems here. You can see it later. Segments intersection to see if they have intersection or not, and at which point they have line intersection again. Side off. I don't know what it is, but let's see. Okay. So suppose that you have a line and you have a point, and you want to understand if the point is on the right side or on the left side. I mean, right or left, it doesn't matter. +1 on one side, -1 on the other side. And you just have to do the cross product for that to understanding which side to choose. And it's doing that for you. Okay, on segment, I don't know what it is. Line transformation, don't know angle, don't know, and I think it's not something to see together now. Circles, intersection of circles, it would give you the points that they intersect. Tangents, okay. Polygon, intersection. I mean, these are all famous that they have the description. These are all famous problems. Yeah. Okay, but let's forget about circles. We have polygons. Is this inside the polygon or not? We have it here. We have the area of the polygon. So, for example, maybe there would be a question that asks you what is the area of the convex hull. You calculate the convex hull using this algorithm here. Then you just call the polygon area, and get that. Polygon cut. I don't know what is it, but I guess it's a famous question. A vector with the polygon with everything. The line going from S to E cut away. Okay, so you're just cutting the polygon with the line from S to E. What is the center of polygon? Okay, the most important one, hull. This is the convex hull algorithm, and it would calculate the hull, and it is sorted. The output is sorted, and it's giving you the points, the boundary points of the convex hull in n log n. Really good. Hull diameter, maybe it would be useful. I don't know. Point inside hull, maybe it would be useful. Line hull intersection. Okay, and that was all the geometry. No, closest pair. Okay. Yeah, we have endpoints in the coordinates, and we want to find the closest pair of points. N square is the obvious solution, but there is an n log n solution that you can find here. It does something with lower bound and sorting them and things like that. And
Can you use sweep lines in some problem set?
yeah, I think there is also. I think there was a divide and conquer thing too. I don't remember, to be honest, but I mean, just copy it if it appeared somewhere. Even on code portal, we can copy it.
Yeah, I was thinking about it.
Yeah. KD3, I don't know what it is. And I'm not that good at geometry in CP, so maybe you would need it. But I mean, it's too much, so I wouldn't read it. Again, this one, I don't know. Okay, 3D. 3D, if there is a 3D problem. Yes. Oh, skip it, yeah. Strings. Okay. Okay. We have 1 hour. Let's start with hashing. I mean, do you know all what is hashing? I think you know. So we hash substrings to see if they are equal or not. I mean, if you calculate hash of each substring from 1 to each element for each I, for calculating the hash of a substring, you just get this one and subtract the hash of here, which is multiplied by base to power length. Okay, this is the thing. Yes, I have a HI. This hash of this. Okay, what is hash? Maybe you don't know that. This is the thing. S0 plus S1 divided by base. S2 with B2 plus all modulo n. This is the hash of substring. Okay. You can also hash it in the other way. You may say that this is Si and -1 and -2, and this is better. Okay, so because you have the string like ABC, and you want this be the 0th digit. So this is C plus base multiplied by B plus base to power 2 multiplied by A.
Probably it's a stupid question. Can you get this string having the app?
No.
You can go back.
Hash is just one way.
It would be really easy to attack you.
Okay.
You could reverse the function.
Yeah, I mean,
Okay.
it's another concept. It's encrypting and decrypting instead of hashing.
Okay.
You can do it.
Yeah, okay. Not in CP, come on. And yeah, so this is okay. What? Okay. So you know HI, okay, and you want to understand this is the string. Yeah, and you want to understand what is the hash of this substring inside. The thing is that look at the representation in the base B. All of these digits are the same. So you just have to cancel these digits. Okay, and these digits again, we have the digits. So if you see this thing, if you see h of L minus 1, you have the same digits in the same order, but all of them have to be multiplied by b to power of something, because you have to move the bits. And what is the something that I was mentioned? It's the length of the substring. So the contribution of h of L minus 1 to hr is b to power r minus L plus 1. That's the thing. So you can easily understand the hash of the substring. And this is the hashing, and you use it to compare if two substring or strings are equal or not. Okay, hashing is something something reliable. So if the hashing of two strings is not equal, for sure they are different. But if they are equal with a good probability, they are again equal in sense of being strings. But sometimes it's not enough to do the hashing only with one mode. So you have to do double hashing or something. And that's why I have the implementation of hashing for you. So this is an easy version. These are the modes that you are using, and the number of them, you can put it anything. I mean, I put 2 for double hashing. You can 3 for triple hashing. Yeah.
Is this the function you use for the problem at SPC? Where the DP with the strings, where like you have to cover on the first one long one. So you hashed like each, let me say, stamp, each of the shortest strings, and every time then you check in the longest one.
I didn't get it actually. What's your question? It's the same as Italian CPC.
Yeah. Um, So for the hashing, which numbers should we use as modulus and base?
Okay. For having the good distribution of the hashing, there should be coprime. So I use all of them as primes. So these modes that I'm using, both of them are primes. You have also some other primes that you can find in the notebook. And also for the base, I put a prime. But I'm not sure how important is that, but this is prime and it's working good. So these are the trusted numbers. Okay.
Okay, thank you.
Yeah. And then I have an init pod which I'm calculating the power of the base to I for each hashing, for each different modulo. Then I have the init hashing which I'm doing the same thing. So this is the most important part. Hash of the first I character is hash of the first I character minus one I minus one characters multiplied by base because you move the digits, and this is the first digit. Always put plus one, because if you just do it, you are if you just forget about one, you are mapping a to zero, okay, and you are mapping nothing also to zero. So another string with length which is smaller than this one would have the same hashing. So the digits should start from one.
Also, AAA
And then
would be 0, right?
yeah, unless AAA would be zero. This is the thing that Pascal said. Yeah, and this is the hashing. I mean, this is the thing that I mentioned, that I'm just subtracting this contribution of this, which is itself multiplied by power of base to r minus l plus 1. And this is the whole hashing. Hashing is really strong, and you can use it instead of KMP and other algorithms that have other functionalities. So the most important part is hashing in the strings, I would say.
Aren't you divided by the base that's important?
No, you don't need it. No, you don't need it. Why I don't need it? Because I define the hashing like this one. If you define it in the opposite sense, you may need it. Because you have to. The thing is that these bits are equal, right? And these are the ones that you have to cancel. Okay? You don't get it? You get it, okay.
Or it's SI plus SI does not have a base. Like SI does not, the last character is not multiplied by the base.
No.
Oh, I don't.
Yeah, if you do it in the other way, you will have that problem. And you
Yeah,
should have
I always did it in the other way.
Yeah. And it's so.
Okay.
So longest prefix of is KMP.
Anima, sorry, but why did you use like two modulus, two primes as modulus?
Because for having double hashing, so it's more reliable. Because for a single hashing, sometimes it happens that the hashing is the same, but the strings are not actually the same.
So you check if both hashes the same at the end? Okay, thank you.
Yeah. So I think also let me show you another thing. So this is palindrome hash. I mean, for checking if an string is palindrome, you have to hash it once from here to there, once from the opposite. Okay. And if these two are equal, this is palindrome. Okay, here I have the comparison. I mean, is palindrome. I'm going through all the modes. I'm going for all. If I'm doing the double hashing, I'm checking twice if the hashing is equal or not. I also have this implementation here. You can look at it later. But again, here I don't have any inverse. As you can see, I somehow dodged it. What are I saying? Okay, KMP. Let's see. Okay, let's start with Z function. Z function is doing this thing. Computes the length of the longest common prefix of Si, and x expects z is equal to 0. So again, longest common prefix, and this thing. Okay, these are the values, and it calculated like that. If it was useful for you, it's on and just do it. I mean, I wouldn't go in details on how it does it, but LPS. KMP for each I it calculates what is the maximum prefix. So for each prefix, you understand what is the maximum length of prefix, which is exactly the same as the suffix. So something like this exactly. And it calculates it in a good way. Yeah, this is saying the same thing, and you would run it and you would get the things. And there are some problems that could be solved with this. I mean, if you wanted to see if let's say that you have a string s and you have another string t, and you want to see if t is substring from if t is a prefix of s or not. I mean, this is stupid, but I'm just saying. You would just create this another string which has s here, an unknown character, and t here, and you would run kmp, and at the end, if LPS of this is exactly t, it means it's the prefix of the other one, or something like that. I mean, why do I say that? I mean, let's say that we want to see in the opposite way. We want to see, we have S and we want to see at which places S was appeared. Okay, the thing we do is we put T hashtag random character S, and the thing is that if T is appearing in somewhere in S, the LPS of this point is exactly T. So just by doing OM, you will understand all the appearance of this substring T in S. Did you get it? And yeah, this is the KMP. The thing it does. Yeah. I can also give you my implementation of that. I think it's cleaner. Then there are some other things. I mean, string problems again. Just read them, and if they were useful for you, use them. But hashing is the most useful one. Suffix array. So I wouldn't tell you what is suffix tree, but suffix array. Please read here. Hmm?
But that's longest common prefixes for neighboring.
Okay. Okay. Let me explain myself. The thing is that So you have a string S. You have a string S, and for each suffix, you have all the suffix. Okay, and let's say that you could sort all of the suffix. Okay, so we wanted to sort all of the suffix of this. I mean, B, A, B, B, A, B. I don't want to write all of it. And then we sort it lexicographically. Okay? This is the thing that it's doing. But I mean, for sure, we are not writing the substring. We are not writing the string. We are just writing, okay, this is the, let's say that this is the sorted version, which says 4, 5, 7, 1, 2, I don't know, 4, 1, 2, 3, 4, 5, 1, 2, 6. Okay. This means that the one which is the minimum one is the suffix that starts from index 3. Then the next one is substring that starts from 4. And why is it useful? Because I mean, let's say that we are uh, let's say that we are looking for another string t, and we want to see how many times t appeared in S. Again, the same problem. The thing is that we can do somehow a binary search in the lexicographical order to see, okay, this is the first one, larger or equal to t in lexicographical order, and then we would have an upper bound. Okay, this is the one that is strictly more. This is lower bound, upper bound, and all the elements here they had the first character equal to t. So these are all occurrences. Yeah, something like that. So because you have all of these sorted, you can do binary search and things like that, and you will benefit from it. That's the idea. There are also some other ideas in it, but I think we don't have much time to cover them. And again, hashing is the most important one, so it doesn't make sense. Okay. Algorithmic. Okay, let's read together this. Read it for yourself. Think about something. I think this is not the best way to research. Let's search it here. Okay, now we'll try. Why didn't you explain the problem itself? Just went to the solution. Yeah, okay, this is a.
Link a overlap. The string overlap in the text.
Yeah. Okay, the thing is that I still remember I said that for each prefix we were saving in the game. We're saving longest prefix suffix LPS. Longest prefix which is also suffix, longest size. The thing is that let's build a try. Do you all know what is a try?
I
Yeah.
don't know what it is.
Okay, so put me wrong. Okay. Let's start so another to try. Try is really just an idea and you can implement it by yourself. Okay, the thing is that we have some strings, okay, and let me go to the solution. I don't know the actual problem. We have some strings. The way we build the try is this one. We have a tree that is starts with with node 1, which represents a string 0. Not 0, I mean nothing. Okay? Then for each first character that appears among the strings that we had, we create a new edge. So like here, we have A. So this node represents a string A. Okay. Yeah, this is the try. Okay, so on the edge we put the characters that appeared among the strings that we had. So we had many strings in the dictionary, and we are putting all of them in the same structure as a tree.
So the strings we want to match.
Yeah, to match something or anything. Yeah. Generally, we have a dictionary, and we save it like this. Okay, in this structure of the tree. Now, for example, for two of the strings in the dictionary, you can easily understand what is the maximum prefix that they have in common. This is LCA. Yeah. And many other things. So the thing is that once you created this and you had another string and you want to see all of the appearance of one of those strings in the dictionary in this one, the thing you need to do is that consider the first character. So we have a new string. This is dictionary. Okay, because it's dictionary. We have a new string and we want to understand all of the appearance. Let's start from the first. First we are here. Then process the first character of the new string. If it's not among these things, we don't have any prefix starting from that saying anything. Otherwise, let's say it's A. So we go here. I mean, you are going a path in the tree. And each time you also start from a new prefix. So, I mean, if you want to, let me think. So how to solve that problem with that? Let's read. Okay, let's think. But I mean, this dictionary helps us to understand for each I, what are the ones that have this suffix? What are the suffix that?
What are the characters? Like from the root for each you said for each character. Which character?
So, for example, these
Like T, A, and I. What are?
these are all the possibilities for the first character of the strings in the dictionary.
And do we store them like in a sort of vectors for each?
No, this is just
it's given
edge, right?
If I understood, you have some strings.
Yeah.
There are special strings you want to find.
Okay.
On the basis of those strings, you build the tree.
Oh, okay. So maybe
the root is just an empty string. Then the nodes that go directly from root are the first characters of each string. Of each special string.
Okay. So it's
then you have the continuations and so on. So it's easy to find LCA, which is common prefix.
Yeah.
That's what I got.
Yeah, exactly. But let's try to solve this problem with that.
Però non capisco una cosa, no? Se due string, ad esempio, la prima string, ci sono solo due special strings. La prima inizia con A, la seconda con B.
Il tuo albero è radice vuota, un nodo che va ad A e un nodo che va a B.
Però se poi la prima stringa dopo la A c'è una I,
L'albero è radice A, I,
B, non c'è la I, cioè non è una
non c'è
possibile
il B, no, perché
seconda.
dovrebbe essere
Ok, ok.
Yeah,
Quindi
exactly.
di proprio esattamente le stringhe.
Yeah.
Sì, ogni percorso, each full path should be one of your special string.
Ok.
Yeah, exactly. Each node is representing at least one prefix of one of the special string, right?
What are we doing in the original problem? Finding
all
the coordinates of the special string.
Thinking. I lost my skills. Okay, I don't know. Sorry, I had to revise it. So maybe I can tell it later, or maybe you can read the solution. But okay, that's the idea. The idea is okay. This is the try. Okay, this was the whole try. Now outcrossing, the thing that outcrossing does is that you are building the try for the strings, and again, like we were computing for the prefix of the KMP, the longest prefix suffix. For each node in the try, we are doing the same thing. So, for example, this is the node, and this is a string from the root to here. And for this one, we calculate the longest prefix, which is equal to suffix for that. And we do it in an efficient way, using BFS. Okay, so we can calculate ethics of all of them, all of this, and this would be really helpful to understand the appearance of the dictionary strings, special strings, in the string which is given, which I cannot show it to you how, but maybe later. Sorry. Then okay. Anything left here? Okay, no. Interval. It has the interval, I think, intersection and things like that. Okay, this is not important. You can, if you needed it, you would implement it by yourself. I think so. And can research. Do you know what is can research? No. Can research is doing the things like that. You have a convex function, or I mean, how would you call it? Convex or the other thing? But the slope of it is monotone. Okay. So the thing you are doing, you want to find minimum here or maximum here. The first thing that you can do is do the binary search on the slope. Okay, because this is the first time that the slope would be positive. This would be the first time that the slope would be negative. So we can do the binary search on the slope. But also ternary search, which is another thing. You would have this function. You want to find the maximum. You get 1/3 of the interval or 2/3 of the interval that you have. You just get the average of L and R current L and R with 1/3 and okay. Did you get it?
Yeah.
Okay. And then you put it like this. The thing we know is that the one which is lower than the other one, the answer is not here in this part. So we just set L to this. T1. Not mid, T2, I don't know. And so you just cut one third of the interval each time. So in logarithm of 3, logarithm of 2 divided by 3 of the size of interval, you would get the answer. But there are many problems with research because, for example, suppose that we have something like this. Okay. If you do the Terry search, this is kit, one, this is 2, and you are comparing these two are exactly equal, you will remove one of the sides, which is okay, right? But it could also appear that you are getting these two, and these two are equal, and you don't know which one to exclude, and you may exclude these parts, and you may lose the maximum. That's why the Terry search, if you are using it, you should be really careful, especially in the geometry problems. I tried them in some simulations, it was not working. Backtrack and recursive. I mean, for brute force, uh, brute force solutions, you just check all of the. You know how to do backtracking? You just do a recursive function. Yeah, okay. Checking all the permutation. All permutation. There is a special function in C++ to generate them. This is the way. So next permutation, you just do while next permutation and do the brute force here. Why am I saying this here? Because maybe you would need to do the naive solution to some of the problems to the tester, and this would be useful. So remember it. All of these would be in recording, so you can refer to it later. Fast mode. As you may know, getting something modulo another thing is really slow, and if you do it many times, like 10 to power 7 times, it's super slow. So there is something in the notebook that I saw which is fast mode, and you can use that for a faster mode. Yeah, this is calculating the mode of B modulo M using something that I don't really understand, and it's a lot faster. I have also another implementation of fast mode, but it's much longer, so yeah, just go with that one. Here, there is also fast input that you may use, but if it happened during the SWERC, most probably you have something wrong, because this shouldn't appear in SWERC, okay? It may help you to solve something. For example, in one of the simulation, I solved one problem with one solution that was not supposed to be accepted. I mean, in those cases, you may use something like this. Yeah. Then some optimization tree, bit. This is the thing that is used in Fenwick tree. X and minus X gives you the least bit in X. Nothing special. Pragma. Okay, this is a good one. Sometimes you need to use pragmas to make your program faster. Pragmas would do something based on the definition of them. For example, yeah, there can global performance of vector is good, but causes crash on old machines. Okay. Uh, hmm? Oh shit. Not the best place. Yeah. Yeah, the thing is that your solution is already run with O2, one of the flags of the program, as I showed you at the beginning today in the morning. And you may use also OFAST or other things. There is also another important one, which is unrolled loops. Yeah. Okay. Oh. You can read this blog actually. Yeah. These are the things that people use and they explain what it does. unroll loops, it's used when you have some simple iterations with for. So you have two cores, one inside the other one, but they are doing really simple calculations. And in those cases, it works really well. There are some architecture reasons behind it that let's skip. Yeah, but these are the use cases. O fast, try all of them. In your case, try O fast, see if it's faster. O3, see if it's faster or not. Unroll loops.
How would we use it?
You would write it at the first line of the.
Yeah. Oh, I just
Yeah.
actually inserted in the code.
Yeah.
Like
Small
define.
Yeah, just like.
Okay.
Yeah, but I mean, don't submit it too much. Test it locally to see. You will get much more penalty then. And that's mode, okay. These are not important.
Is penalty applied only if you solve a specific problem?
Yeah.
So I can get minus
Yeah, exactly. Perfect, yeah. Okay, so let's see. I think that was all. Grandi number. Forget about it.
Yes.
Yeah. Bit set, I said. There was something from graph part that I didn't mention. Euler tour, I think it wouldn't appear. Two sets is good, but it wouldn't appear. If you wanted, you can. No, never. Maybe. Small to large merge, okay. It's a trick, like the trick that we use in the DSU, okay? Whenever you have two sets and you want to merge them, the way to merge them, which would be optimal, is that keep the heavier one static and don't change that. And for the smaller one, iterate through the smaller one and add it to the other one. So for example, if you have two sets and one of them is larger, you want to merge them. One of them is larger. Keep that there and iterate over the other one and add it to there. And then when you use the smaller one, clear it to free up the memory. So you wouldn't get the memory limit. This way, exactly like DSU, the total complexity of the merge would be n log n. So you may use this in many areas, but especially in trees, when you have some data structure from subtrees, so you are calculating something for a subtree. You would do it recursively for the children, and you would have a data structure. And you want to merge these data structure. The way to merge them is always keep the larger one static and apply all of the others to the one. That one. This is the smart to large merge trick. SAC. If you wanted, you can search on Code Forces. There is a blog about this SAC. It's called SAC. I think it's not the best name, but and to DP forget about it.
And multiple dimensional DP. Like 3 or 4 dimensional DP.
2 dimensional.
Yeah, I mean there are also problems with 5 dimensional.
Yeah. There could be. I didn't say anything because I suppose those are things that you can think about.
Okay.
These were strings. Misc. Good luck. Yeah. Is anything I missed? Hashing, memory, modules. Forget about modules. EFSS, SCC. I will share the code of that, and also I will share the code of compare function. I mean comparator. I don't know how to say that. That you can give it to the sorting.
Yeah.
Comparator.
Boolean comparator.
Yeah, the Boolean comparator.
Yeah. It's like a function pointer.
No, it was just compared to two things. And for example, two pairs. It's operator to compare them, and you give it to the sort.
You can use a function pointer.
No, you don't need the function pointer. No. It's overkill. I mean, no. You are actually giving the function pointer, but you don't. I didn't know it until now.
I tried to do something like that in a past problem. So.
Yeah. It's the same. Yeah. Okay, that's it. Good luck. Guys, do you have any question? No?
Quindi si può fare davvero.
No, it's okay. It's okay.
Yeah, it's okay.
I will ask you something maybe later when I study it.
Non so come funzionano gli altri ma
Ok.
spazio fisico.
Ok.